Okay, very good morning, everyone. Welcome to another HSMA training day. Today we've got a couple of different things that we're going to be covering. You've got me for both sessions. You'll be delighted to hear, I'm sure. So this morning we're going to be going through SimPy, the last of the discrete event simulation sessions. And then this afternoon we're going to be talking about cellular automata as we introduce behavioral modeling, particular research interest of mine. So lots of different stuff today. So this afternoon will be quite sort of weird and abstract and getting you to think about some potential ideas. And then this morning is a bit more technical, because obviously in the last session in this module, you had some practice building your very first model, your very first discrete event simulation. You all did a fantastic job at building these discrete event models. And so in this session, we're going to take this a little bit further, mostly centered around showing you how to put the SimPy models into an object-oriented structure. I mentioned this in the last session that as you probably saw, you were getting a bit fed up of passing things around across the functions, etc. And this will do away with all of that and make things much more elegant. So we'll show you that. Most of the morning, though, you're actually going to be working in your groups and building a model. So you're going to put all of this into practice, both the skills you learned last time and the new skills from today as well. So you'll get a chance to really have a go at this, and hopefully you'll find it really satisfying when you manage to build a model this morning and get it all working, and hopefully that should be really good. And I'm also going to, there's a couple of little tutorials, pre-recorded tutorials that I'll get you to watch at the end, just very short, sort of 10-15 minute tutorials, where I talk to you about a couple of concepts in SimPy that we haven't yet covered, things like prioritizing a resource, prioritizing somebody in a queue, so you have priority queues. We talked in the very first discrete event session about sometimes you may want to have, rather than a first in, first out policy in your queuing, you may want to have people who are prioritized, and very often that will be the case in the particular settings that you're looking at. So I'll show you how to do that. It's actually really easy. And also looking at modeling unavailability. So when your resource it becomes unavailable for various reasons, and ways you can do that, which I sort of briefly touched on, I think, in the last session of this module, and explained how you do that sort of theoretically. And this is, I'll show you how to do that in SimPy. And again, it's pretty easy. Okay, so let's press on with today's session. So up to this point, when we've shown you SimPy models, we've shown you the what's predominantly a sort of non-object oriented way of putting these things together. There is some object orientation in them. You'll remember when you set up a resource, for example, in SimPy, you set it up as an instance of the resource class. So there's some elements of that. But I've deliberately not shown you the kind of object-oriented way for two reasons. First of all, because this is the way that SimPy, the SimPy tutorials, which are okay, I don't think they're great, and there's actually quite poor information out there about SimPy, so I'm quite proud of what we do here with this. But that's the way they do it. They gradually build you up, and they don't start with the object-oriented thing, and I think that's the right approach. And the second reason is because at the heart of SimPy, as hopefully you've already seen, are these generator functions, which we talked a lot about last time. This idea that there are things in Python called generator functions, and they're like normal functions, except you can kind of freeze them in place and create instances of them, and you can have different functions, different instances of that generator function, all at different positions, and then you can freeze and unfreeze them at different points in time. And that turns out to be really useful when you're modeling a discrete event simulation, because it means you can have generator functions to represent the discrete event generators that are creating new entities coming into your system, but also to represent kind of your entity journey, so patient journey or whatever your entities represent through the system. And so you can have them at different points in the process. So the point of showing you that first is because that's still at the heart of SimPy. So even with the object-oriented structure, you'll see that it's still based around generator functions. It's just we tidy it all up a bit. And the thing, as I say, you've probably noticed, even in the relatively simple examples that you were working with last time, is that you had to pass everything around to all the functions. So when you started up your simulation, you had to start up your generator functions. And even if you just have one, that was a bit of a pain, and particularly if you had lots of, so you had to pass in all the inter-arrival times and the resources that you need and the activity times and the environment, and then the generator function for your arrivals would then have to in turn pass most of that on to the journey. Now you can imagine, I mean, it was getting a bit of a pain just for modeling 2 or 3 activities in a relatively simple system. So you can imagine how much of a headache that would be if you try and create anything more complex. So the object-oriented approach will make this much more elegant. I would highly recommend that you adopt this approach. It can seem a bit overkill if you're just doing very simple models. So I'm aware that in the example that I'm going to show you in a moment, for example, which is a very simple system that we looked at last time, you probably look at that and think, well, that's more complex because suddenly I've got loads more code that I have to put in. It might be a bit more elegant, but it's still, I've added to my troubles, and that's because it's really built for that kind of structure is built for more complex models. But remember, when you come to build these things, you're likely going to be building slightly more complex models than we're showing you here, or at the very least, you kind of want to future-proof them so you can add bits in as you evolve the model. So I'd recommend going down and getting used to the object-oriented approach. If you find you can't, and you want to stick with a non-object oriented approach, that's valid. I mean, you can take everything you learned from the previous session. That will allow you to build SimPy models, and I have done that using that approach before. So, but if you can, I would advise sort of switching over to this particular approach. Particularly as well, I think, one thing we try to instill in you in terms of the Python training is that as coders, really, you should be looking to make your code object oriented wherever you can. It does make it much more elegant in modern times, really. That should be the gold standard. So we've talked about why we want to do it. Let's now look at how we would do it in theory. Now, the other important thing to say about this is that there are multiple different ways of building an object-oriented SimPy model. Again, the way I'm showing you here is the way that the SimPy tutorials advise you to do it. That doesn't necessarily mean it's the best way. And in fact, within the team, I think there are 2 or 3 different ways in which members of the team do it. And arguably, some of those ways are slightly better. But to avoid confusion, I'm showing you the official SimPy way. But as I say, don't feel free to play around with that, and if you find other approaches work better and more elegant for you, then that's absolutely fine. The key thing is to put this into an object-oriented structure. So the way I'm going to show you is basically the kind of the SimPy official way, if there were such a thing. Okay, so this is how we're going to structure our models. So what we're going to do basically is we're going to have 3 classes. Okay, remember when we talked about object-oriented programming, classes are blueprints from which we can create instances or objects. So we're going to have 3 classes in our SimPy model. The first class is going to be called G, lowercase g. Now, this is a bit of an unusual class, and I hinted at this much earlier in the course. This is an example of a class where we're not actually going to create any instances of this class. We're going to refer to the class itself directly. And you'll remember from the object-oriented training that I told you very, very rarely do that. Usually, you should always have the class as a blueprint, and then if you're working with it, you should create instances of that class. But there are some circumstances where you may wish to create a class and then you refer to it directly. You don't actually create any instances. And that's because what this class is doing is it's basically holding all the global parameter values that you're going to need across the model. So we don't need to create any instances of it. It's kind of like a little, it's almost like, I don't want to say database because it's not, but it's a little holding pen where we can stuff all of the information, including all the stuff that we were shunting around before between, sort of functions. We can just dump it all in here. And say these are the global variable values, and if you need to refer to it, they're in there. Okay, so it's like the storeroom for your parameter values for your model, and that's G. So basically, it won't have any methods. Well, it's unlikely to, but it will have essentially a series of attributes, and these will represent global parameters. There'll be things like your inter-arrival time, your different inter-arrival times, your maybe a number of nurses, how many runs of the model you want to do. I mean, that kind of thing. All of that will stuff in there, and we can just refer to it anywhere we are in the model. Okay, so that's really useful. That stops us having to do all that passing around rubbish. The second class that we're going to build, so that's the only class where we're going to deal with it in that way, and we won't create instances. We'll refer to it directly. These other classes, we will treat them as we would any other class. So we'll have a class for each type of entity in our model. Usually that will just be one type of entity, like patient or whatever, but you can have, as we talked about, you can have multiple different types of entity, and sometimes you may want that. And so you have a class per entity, basically. So if your entity is patients, then maybe you've got a class for patients. And each of these classes will have certain attributes, and those will basically be the things that those entities carry around with them. So like the patients we saw last time, we were sort of assigning a patient ID to each one. You may have a patient ID, or it may have additional things like their condition or their age and things like that. Okay, so these are attributes that are carried around by your entities. And you may also have specific methods for those entities as well, or it may just be a constructor. Remember, you have to have a constructor. You don't in class G, because we're not actually going to construct anything. We're just going to refer to that class, so it'll never create an instance. But in this class, we're going to need a constructor at the very least. You may need nothing else, but you might have particular methods that you want to put in for that particular entity. And then basically what we'll do every time a new entity, for example, your patient arrives, we'll create a new instance of this class. So our arrivals generator will essentially be creating new instances of this class. Okay, which already seems a bit more sensible than what we were doing before. Where, remember, before, what it was doing is the arrivals generator was creating a new instance of the patient journey generator, which was kind of working as a proxy for creating a new patient, but it wasn't. What it was just doing is creating a new function, a new instance of that function. So here it almost makes more sense, really, I think, that you're essentially your generator generating your arrivals will create a new instance of your entity class. So we've got at least one of those. If you've got more than one entity, then you'll have a class per entity. And then we've got a class representing our model. And so this model class, again, will also have attributes and methods. The attributes will store things like the simulation environment and any resources that are used in this particular model, so your nurses, doctors, whatever it may be. And then for your methods, we'll have the constructor, obviously, because we're going to create instances of this. We're going to have one or more entity generators, and that will be, as we wrote them before, they will be generator functions. So there'll be essentially generator functions within these methods that will create your new entities, which will now be classes. We'll have one or more sets of generator functions describing the sequences of events that will happen, so your pathways, just as you did before. And we'll have a run function that will basically start up the entity generator or generators, and will run the model for the required amount of time. So that's the basic structure. So you've basically got a class G that will hold all of the the global parameter values that you may need to access wherever you are in the model, but we're not going to create any instances. We're just going to refer to that class directly. It's like a little storeroom for our variable values. And then we've got a class for each of our entities, so a class per entity, which will probably, as I say, mostly just be one type of entity for the stuff you're doing. And then we have a class representing our model. Okay, so let's go back to see how this will work. Let's go back to a really simple example that we looked at last time. This was the first model that I showed you how to build in SimPy, where we've just taken that really, really simple system where we've got people arriving for a weight loss consultation, they queue up to see a nurse, they have that weight loss consultation, and they leave. Okay, so really simple system, single activity, single queue, one type of entity, one type of resource, just so that you can see how you would do that in an object-oriented framework. And as a reminder, this will look like a little bit like overkill, because it's you're having to put a very simple model into an object-oriented framework, but hopefully you'll see it's still, I think, much more elegant. Okay, so essentially this is how we're going to structure this. So we're going to have our class G. Remember, that's going to store our global variable values. So that will store the inter-arrival time, which I'm going to set to 5 minutes, the mean consultation time, which was 6 minutes, my number of nurses, so I've got 1, how long I want the simulation to run for, so 120 minutes in this case, and how many runs of the simulation I want, so in this case 10. So all of that global stuff that I want to be able to access from various points of the model, I can stuff it in there. And then I'm going to have a class representing my weight loss patient. I've called it weight loss patient, even though there's only one type of patient in this model, because remember, that little model that I've shown you there came from a much bigger model that in reality we might want to build up to that, where you had different patients, some arriving for tests, some arriving for the stop smoking clinic. So you may want to have different types of entity. So just to future-proof it, I've made it clear that these entities are our weight loss patients. And then those patients, they're going to have just a single attribute. They're just going to have a patient ID, as we did before, and they're just going to have a constructor method. There's not going to be anything more than that. And then I'm going to have a class which represents my model, which I'm going to call GP surgery model. This will have 2 attributes. One will be the environment, the SimPy environment, and one will be our nurse resource, which will be a SimPy resource. Okay, so we've got a SimPy environment and a SimPy resource. And then I'm going to have my methods. I'll have my constructor. I'll have the arrivals generator function, which I've just called generate WL weight loss arrivals. I'll have my patient pathway function, so a 10 WL clinic, which will describe the series of processes they'll go through, and then a run method, which will basically tell these things to run in the correct order. Okay, so let's have a look. That's how we're going to do it. Let's have a look how we translate this into code. So I'll talk you through how this is structured. I'd also encourage you as well to have a look at this after I stop talking. When we come onto the exercise, have a good look at it and make sure you understand how it all works. It's not quite as complex as it may first seem, and hopefully that by seeing this structure here, that's given you an indication of that. So a lot of this will actually look quite familiar, because it's very similar to what you were doing before, just we've structured it a little bit differently. So as before, I've imported my SimPy and random libraries first of all. Those are 2 very common libraries that you will import when you're doing discrete event simulation. You need SimPy to do all the structural stuff, and usually you need random to sample from distributions. You'll probably also want, in reality, things like NumPy and pandas and stuff when you come to do this for real as well. So then we've got our first class. Remember, this is our G class. This is the one that's going to store our global parameter values. Remember, we're not going to create any instances of this class, so we don't need to specify a constructor. So literally, we're just going to have it as a kind of holding pen for our parameter values. And remember, before, when we were doing this, we just basically stuff those at the bottom and then sort of pass them into the arrivals generator. That's not what we're doing here. We're just holding them here so that we can just refer to them whenever we like. So we put them in class G. So I've got my inter-arrival time, consultation time, number of nurses, simulation duration, and a number of runs, and they're all there, and I can access them at any point in the model, as you'll see. So then I want my class that's going to represent my my entity, which I've only got one type, and it's a weight loss patient is my entity in this model. And again, all we've got in this particular class is a constructor and with a single attribute, and that's going to be the patient ID, and we're just basically going to set that up, and we'll pass in a patient ID when we create a new patient. We'll give them a patient ID in this particular instance. So all we do here is pass in a patient ID and tell it to store that as its ID. Okay, so very simple, nothing complex there. And then we've got our class representing our model for the GP surgery. And this is basically where all the stuff happens. So this is where you'll see most of the stuff that you were doing before. So the first thing we need, as with all classes where we're creating instances, is a constructor. So what the constructor will do is it will set up the SimPy environment. So you did that before when you were doing the other the non-object oriented approach, but here we're doing it within the constructor. Now, because it's object oriented, remember we have to refer to self to say it'll be the instance of this, because we're going to create an instance of this GP surgery model. So it'll be that instance of the model that we'll refer to. And so that's what we need to why we need to use the self keyword. So we've got self dot environment equals SimPy dot environment. Now create a new SimPy environment and store it as an attribute of this model. I'm going to have a little patient counter attribute there, which I'll start at 0, and then I can just increment that each time a new patient gets generated, and I can give that as the patient ID. As in reality, you might want to do something a bit more advanced, but this is just allowing me to keep track of different patients. And then I'll create my resources. I've only got one resource here. I've got a nurse. So I'll create a new nurse resource, just as we did before, SimPy.resource. Just a couple minor differences you have to remember when you create a new resource in SimPy, you have to pass in the environment in which they will live, which is obviously is env, but it's now stored in the instance of this model class. So you need to remember to put self.env. And the capacity, before we were just hard coding that number in here. Now, remember, we store that in our G class. We've got it up here so that we can easily just change it up here. So it's to refer to that G class, we don't create an instance of it. We just refer to the class directly. So we just say G dot, and then we can access whatever attributes or methods. And so number of nurses will grab us out that number there. So I would change that to 2 up here. Then that'll change it down here as well. Okay, so that's all that's doing. That constructor is just setting up a new environment. It's stuffing that in the environment attribute of this instance of the model, setting up a patient counter starting at 0, and creating a new nurse, and again stuffing that in this model. So the model's now got an environment and a nurse. So then we set up our method for our arrivals generator, and this is very much as you saw it before. So you remember when we talked about this before, we showed you how to do this. You basically set up an arrivals generator, and you get it to essentially create a new patient, and then get it to process that patient, and then sample the time until the next one, and then freeze in place. And that's exactly what you do here, just with a couple of minor differences. So we still put it in an infinite loop while true, which basically just tells it to keep doing this until the simulation ends. Obviously, if you were, just as a side note, obviously, if you only wanted arrivals for a certain time period in your model, you could do that as well. So you could just put it in a particular for loop or while the simulation time was below a certain amount or whatever it may be. But this, in most cases, you're probably just going to want to keep generating arrivals until the simulation ends. First thing I'm going to do is increment my patient counter by 1, so that my first patient is patient 1, just to make it a bit more readable. Remember, my patient counter is stored in the instance of the model now, so we say self.patient counter. Then I'm going to create my new patient, which looks very similar to before, except this time we actually are creating an instance of a patient class. So we defined what a weight loss patient was up here. It's one of these. So we're going to create one of those. So we say it's a weight loss patient. The thing it needs to be passed in is a patient ID, and we'll use the patient counter as the patient ID. So I pass that in, and I'm going to store that in WP. So that's now an instance of this class. So I've now got an object called WP, which is a patient object. Then I will get the SimPy environment to run the attend WL clinic method, which I'm writing below, which we'll come on to in a second. And that's going to be our patient journey function, essentially. Again, remember the environment is stored in this instance of the model class. We need to keep using self. So whereas before we were saying env.process, we now have to say self.env.process, the environment stored in this instance. And then we pass in the self.attendwl clinic. So that's the name of the method, which again, it's self because it's stored in this class. And then that needs an input of a patient, which we've just created one up here. So that's the patient we pass in. So it's similar to what you did before, but before what you were doing is you were saying create a new instance of this generator function. But here you're actually creating a new patient and then passing that into this method. And it's a subtle but important difference, because that patient, obviously in this example, we've just got the patient carrying around a patient ID, but it allows you then to do much more, because then a patient can suddenly carry around all sorts of information with them. And you can have differentials in terms of how different patients are and the different conditions they have, etc., etc., because you can just create different instances of that patient. So once we've done that, once we set that going, remember that all we've got to do then is sample the time until the next arrival. That's exactly the same as it was before. The only difference, again, is that the inter-arrival time, which before we were passing into this function, we don't want to be doing all that passing around now, so we just grab it from the G class. And then we want to freeze this function in place until that time is elapsed. So that's exactly the same as before. Again, the only difference being we have to remember to refer to self.env because the environment's stored in this instance of the class. But the structure is exactly the same as you saw before. Then we've got our method for the patient journey. So my attend WL clinic function. That's going to need a patient passed into it because it's that patient that will then go through that process. Just as I did before, I'm going to have a little message that prints when the patient started queuing. And then I'm going to request a nurse exactly as I did before. The only difference, again, remember the nurse is stored within this instance of the model. So I need to use self.nurse rather than nurse.request. Then I will yield the request. So that will basically mean freeze this function until a nurse is available. Then I'll print a message saying they've finished queuing, because once you've got to this point, then a nurse is available. Then I will sample the time, just as we did before. How long are you going to spend with the nurse? Exactly the same. Again, the only difference is that the mean consultation time, we're now grabbing from the G class. And then I will freeze this function until that time's elapsed. Again, exactly the same as we did before, just with the minor difference that you're going to say self.env. So that's exactly the same in terms of the structure. It's just you have to remember that where the nurse and the environment, etc., are stored, and where your mean consultation time is stored a little bit differently. But it's much more elegant because you're not having all this stuff here that you've had to pass into it. So we've written our constructor, we've written our arrivals generator, and we've written our patient journey generator. So the only other method we're going to need to run for this one is a method which runs basically what starts all this going. So our run method will basically tell SimPy to start up the generators. We've only got one arrivals generator here, so we just tell it to process the generate WLL arrivals ones. This one that's going to create the new patients. Again, exactly as you wrote before, it's just we've got these self keywords in here. And then tell it to run again, exactly as you did before, just you've got the self keyword because the environment is stored in self. And the time you run until, again, we hard coded that before. Now we just grab it from the G class. So all of that defines our model. All of this that we've written, we've got our G class, which stores our global parameter values. We've got our class representing our entity, our weight loss patient, and our class representing our model, which in turn has stores the environment and the resources, and the constructor specifies the setup of those. It has our arrivals generator, our patient journey generator, and the run method, which sets all this off running basically. So once we've done all that, everything is defined. But remember, we've just defined it. Nothing will happen. We've just told it this is what a G class that looks like. This is what our patient class looks like. Python isn't going to do anything with that until we tell it to. So here is where we'll start to get it to do things. And basically, I'm going to tell it for the number of runs that I've specified in the G class, run this thing. And remember, before you had to put all of that, because all of your setup and all your parameter values were down here, you had to put all of that in a for loop, but now it's much more elegant. So we've got a little for loop, but all we've got to do in that for loop is say for run in range number of runs, which I can grab from my G class up here. I'm just going to have a little print message, which just tells me which run I'm on. I'm saying run +1 so that it's a bit more user friendly, so it doesn't start run 0. And then I will create a new instance of my GP surgery model class. And then, so this one here, which contains all of the stuff within the model, the journey and the arrivals generator. And then I'll just run the run method, which I defined here. That's it. That's all I need to do. That little print message is just to put a little space between these things. And that's it. So if I run that, push F5, there we go, it's run. And so I've got, just as I did before, I've got different runs. So I can see run 9 of 10, run 8 of 10, etc. And I can look at all the details, when the patient started queuing, when they finished queuing, etc., etc. Just as we did before, but much more elegantly. Okay, and you can see now that it's much easier to add things in. So if I wanted to suddenly add in an extra resource, I'd have to worry about passing it in across all of the different functions that it may need to go to. I can just add another resource, another quantity of resource into my G class, and another resource into the model class here. And that's all I need to do. So it makes things much, much easier to do. Any questions about any of that? Good. Okay. Hopefully that's made sense. And as I say, I would encourage you to have a look at it as well when you come to the exercise, just to make sure you can get your head around it. But it isn't quite as complex as it first seems. And if you're used to the way we did it last time, as I say, it's just a slight difference there, but it makes a huge difference, I think, in terms of how this works. Okay. So we talked before as well in the last session about that it's usually important that we're going to want to capture results across a trial if we're going to be running the simulation lots of times, and we want to take a sort of average results over 100 runs or whatever it may be. So to store that, we're going to have to do that slightly differently in our object-oriented framework. And one way in which we could do it, and again there's different ways, we could add a run number attribute to our model class, so that the model always knows which run number it's associated with. And then we pass in that run number when we instantiate that class on each run. So that allows us to basically say, okay, this instance of the model class is run 1. This instance of the model class is run 2. So that'll be really useful when we're storing results. We can add a pandas data frame as an attribute to the model class that will then store those results against the run number. We could add methods to the GP surgery model class that will calculate the results we want to store. We can add a method to the model class that will write the results from the run to file. We can call these additional methods from the run method after each simulation run. We can create a new class that will hold attributes and methods for calculating and printing results over the trial. So we'll have a dedicated class that will do that. We can create a file with appropriate column headers before we start running that batch of runs, and we can instantiate a new class for calculating trial results after the batch of runs is completed and call all the relevant functions. Now that probably won't make sense at the moment, so I'll show you what I mean by this. Again, it's a bit simpler than it sounds. And again, I'd encourage you to have a look at this after I stop talking as well. And again, this isn't the only solution. This is just one way in which we could do it. Let's imagine we wanted to adapt our model that we've just written so that it records average queuing time for the nurse in each run, and then we'll take an average over all of the runs in the trial. So if I look at SimPy 002.py, let's go back to that one. Okay, so imports the same as before, except I'm also going to import pandas, and so I can have a pandas data frame, and I'm going to import CSV, which you remember allows you to do nifty things, reading and writing CSV files really easily. All of my class G, that's all exactly the same as it was before, so I'll skip over that. That's identical. The weight loss patient class has got a minor change. I've just added in one extra. So before we just had a patient ID that was passed in. We still got that, but I'm also adding a little attribute here that isn't passed in. It just defaults to 0, and that's a queue time for the nurse. So basically, each patient can hold how long they queued for the nurse. Okay, so that just means that that'll be easier than when we want to take averages across the patients. Each patient basically has a piece of information they take with them that says how long they ended up waiting for the nurse. So we can ask the patient how long. Other than that, that's identical. So here is a little bit different. So the constructor for the model class, again, all this is the same. The environment that we set up, the patient counter and the nurse, that's identical as it was before. But what I'm also going to do is pass in a run number when we set up a new model. So that basically at each run, we can say this model represents run 1, this model represents run 2, etc. And so I pass in a run number, and I'll store that against an attribute called run number, so I always know which run number this relates to. I'll also have an attribute here which defaults to 0, which just is going to store the mean queuing time for the nurse across all the patients in the model. Remember, each patient object will store how long they waited for the nurse, and then we also want in the model class what was the average across all patients in this particular run. And then I'll also set up a little data frame here, pandas data frame, that will have various columns, like patient ID, the time they started queuing for the nurse, time they finished queuing for the nurse, and the total queue time. In reality, you probably won't need these things. I've just put them in just to show you an example of some extra column headings. In fact, when you come to the exercise, don't do that. You just usually want the queuing time in there. And so I've set up that new data frame. So that data frame is stored within the instance of the model class. So that data frame will basically hold a log of all of the patients and how long they spent queuing. Then we've got our arrivals generator. This is, in fact, I think this is entirely exactly as it was before. So yeah, so I will skip over that. So that's exactly as we wrote it before, no difference there. Slight difference though in terms of the patient journey function, because remember this is where we work out how long patients are spending waiting for the nurse, because this is where all the queuing stuff happens. So I record the time they started queuing for the nurse as I did before. I'll request my nurse exactly as I did before, yield that request, and then record the time they finished waiting for the nurse. Again, you're used to seeing this. I calculate the time I spent queuing as a patient. Again, you're used to seeing that from last time. You just say the time I finished queuing for the nurse minus the time I started. That's my queuing time. And I can store that now, because remember, the patient will hold that piece of information and take that with them. So I'll store that calculation in the patient's queue time nurse attribute. So that patient now has that piece of information. We can ask that patient, how long did you spend waiting for the nurse? Then I'm also going to store the start and end times alongside the patient ID and how long they were queuing in the pandas data frame of this model class, of this model object, sorry. So as we set up before, I'm going to put in my patient ID. So whatever patient ID we're dealing with, the time I started queuing, the time I ended queuing, and the patient's queue time, which I've just stored in the patient. And remember that this is how we add to a pandas data frame. So we create a new little data frame to add with that information, and then append it to our main data frame, which is the one stored as results df. That was the one we created up here. So that'll basically, all that's doing is it's saying, okay, I've calculated how long this patient spent waiting. I will now store that information in the pandas data frame for this this model, this run of the model, and so that information we can access against that patient ID. Then all of this is the same as before after that point, so we just randomly sample how long they spend with the nurse, etc., and wait. So this is new. This is a new method that will calculate the mean queuing time for the nurse across all of the patients in the model. Remember, this is that we're in the model class, so you've got multiple patients who are running around this thing, and all of that. Whenever we call this method, we can say, okay, now calculate the mean queuing time for the nurse, and it will do this in this simple line of code just by saying, well, I'll take the queue time nurse column of my pandas data frame and I'll take the mean of it. That's all it is. That's all we need to do. And I'll store that in the mean queue time nurse. Remember the model class, we added this attribute here that allows us to store the mean queuing time for the nurse. So whenever we call that, it'll say, okay, I'll take the average queuing time for all patients in this run. I've also set up a new method here, which will just basically write these results to file as well, whenever I want to do that. And again, this is all stuff you've seen before. So I'll open my CSV file, I've just got trial results in append mode, so it'll add to the end, it won't overwrite it. And I'll set up a new CSV writer and I'll write the results. Basically, I'll write the run number against how long, what was the average queuing time for the nurse. So what we'll end up with is a file that will say in run 1, there was an average 20-minute wait for the nurse. In run 2, it was 18 minutes, etc. So all of that's exactly as you've seen before. It's just we've written a little method to do that. And then our run method, again, these first two things are exactly as they were before, but I've just added these extra two things. So basically this tells it to start up the arrivals generator. This then tells the simulation to run for the specified amount of time. So that would then be the end of a single run of the simulation. And then once it's done that, I also want to call these new methods that I wrote. So once it's finished a run, then I want to call the calculate mean queue time nurse method up here, which will calculate the average queuing time in that run. And then I'll call the write run results method, which will then write those results to file. Okay. I've also set up a brand new class here called the trial results calculator. And that class is basically going to store, calculate and manipulate the trial results in a pandas data frame. So I've just got a little constructor here, which just sets up a data frame and calls it trial results df. And then I've got a little method here, which will basically read in the trial results that we've been writing elsewhere in these write run results thing. It's going to read all that in after it's finished. We'll call this basically when it's finished all of the runs. And it'll just print out that information to the user. So it'll read in that file that we've been writing to, and then it'll take the average over all of the runs. So across, say we've got 100 runs, it'll take the average queuing time across all of the runs, and then it'll print that out for the user. That's all that's doing. Okay. So remember, everything above is just classes and function definitions. Here's where we're going to do our stuff. This is the same, except I've just put in a little extra bit here that will basically just create this new trial results file and write in the column headers just to make it easier, so that when we read it back in as a pd.read.csv up here, we can use that nice feature where it automatically reads it in as a pandas data frame with the correct column headers. So I've got my column headers written in. I'll write that to file before I do anything. And then I just do it as I did before. So I just tell it to run for a certain number of runs. I print a message saying which run you're on. I create an instance of that model. The only difference here is that I'm now also passing in the run number. So each instance of that model will have a run number associated with it. I then run the model and we keep going around that loop for however many runs I specify. Once the trial's complete, so once we've done all the runs, then I'll just do this extra stuff here, because I've got this new trial results calculator that will sort things out once I've done all my runs. So I'll create an instance of that class, and then I'll just run the print trial results method of that class. And that will basically give me the average over all the results, over all the runs, sorry. Okay, any questions about any of that? Oh, good. Okay. So hopefully that's sunk in. But as I say, do have a look back over the code as well. Make sure you understand it. It's not particularly complex, and obviously this is just one way of doing it, and you may decide to do it different ways. But this is a suggested way that you could use. Okay. Time to go on to the main exercise for today, and you're going to be spending basically the next hour and a half doing this in your groups. So what I want you to do is I'm going to task you with writing an object-oriented SimPy model of this system that I'm describing here. Now you'll recognize this. We talked about this particular model earlier in the course. So here we've got people arriving at ED. They queue to wait for registration with the receptionist, and they queue to wait for triage with the nurse, and then 20% of them will go off to the ACU with an ACU doctor, and 80% of them will stay in the ED and have an assessment in the ED with an ED doctor. And here's all the information in terms of your average inter-arrival times and registration times and all that, the number of receptionists and nurses you've got. I also want you to run the model for 48 hours of simulated time. So use your time units. I'd recommend to consider as minutes. But I want you to do that after a 24-hour warm-up period. So you'll also remember from the last session we talked about warm-up and how we bring that in. So remember to refer back to your notes on that as well. And I want you to run the model 100 times in your trial. So you're going to need to ensure that the model will store the queuing times for each queue for each patient. So you've now got 4 queues. You've got a queue for registration, a queue for triage, a queue for ACU, and a queue for ED assessment. You don't need to, as I just mentioned a moment ago, you don't need to store the start and end queue times. Just store the queue times themselves. And you'll record the average queuing times for each run in a file, and it'll calculate and print the average queuing times results over the trial. Now, I'd recommend that you store the queuing time results for a patient in a pandas data frame, as I've just shown you, and that will be stored in the model class at the end of the patient's journey through the ED alongside their patient ID. However, there's a slight complication here because you've got a branching path in this model. Some patients aren't going to have each patient is basically going to have at most 3 queuing times, because they're not going to go down both of these routes. They'll go down one or the other. So you're going to have some patients who don't have a queuing time for ACU and some that don't have a queuing time for the ED. So the way I recommend you deal with that, because you can't have missing values in a pandas data frame. So I would recommend you do that by replacing the missing queuing time, whichever one is missing. So if they go down to ACU, then your ED queuing time is missing. Replace it with a NaN, which stands for not a number. There's a little handy tip in Python. You can create a NaN deliberately by casting the string NaN, all lowercase, as a float. If you do that, that will create a NaN and not a number value. And the reason you want to do that is because if you're using pandas, NaNs are ignored by pandas when it does things like calculating the mean. So you can just put a NaN in there, and it'll basically just ignore that entry as though it doesn't exist, which is what you want here. Okay. I also want you to deal with the branching path element of this model by having an attribute in the patient class that will store the probability of a patient going to the ACU, and a flag as well, some sort of Boolean flag that will indicate whether or not they are going to the ACU, and also a method in the patient class that will determine whether they are going to the ACU. So basically that's and that will be called after the patient's generated, but before they start their journey. So basically what I'm saying is what you want to do is when you create a patient, it'll have a little method in there in the patient that's called, that we run after it's been created, to say, this is now, I'm going to predetermine whether I end up in the ACU or not. Okay, so that's how you're going to do it. So then and it'll update a little Boolean flag. So that patient will be predestined to go to the ACU or to the ED. And that will be, I want you to do that at the point of generation. Don't forget to include the warm-up period as well, and make sure that you don't store any results that are generated within the warm-up period. However, it's fine that, to store anything where the patient journey starts within the warm-up period, but it will end after it. That's fine. You can count those, and also ensure that your simulation runs for the total amount specified. So you need to run for 24 hours of warm-up and then for 48 hours thereafter. So I'm going to give you about an hour and a half. So we've got to about 10 to 12. I want you to work in your groups. This is not trivial to do this. So make sure you're all sort of working together for this particular one. And do take a break. You may want to take a break now. You may want to take another break somewhere in the middle as well. So do have a break, stretch your legs, and then have a go at this. I'd recommend you read through this again just to make sure you understand this. And have another look at the examples I showed you, SimPy 001 and 002. Everything you need is in there, and that just this little bit of extra information in there about what I want you to do with missing values. Okay, I will set you off. I'll stop sharing. I'll open the breakout rooms, but as I go and stretch your legs first, I would. That's a lot of information, and I'll bounce around the groups, and I look forward to seeing what you come up with. Also, when we come back, I'll get a couple of groups just to present their models. So do make sure you've got somebody lined up who can do that when you come back. Great, see you in a bit. Oh, I think my Zoom's crashed. Apologies, I'm unsure if you can still hear me, but
yeah, we can.
You can. Great. Okay, that's good. I'm going to have to now close down Zoom because it has crashed. This should still keep running. If it doesn't, I humbly apologize. Please just rejoin in a moment. But I think it should keep you in because I had this once before. I will close it now and cross all my fingers. Thank you. I see lots of people still here, so I think everything still worked and the recording's still going, which is fantastic. So, phew, excellent. I'm glad that worked. Although there's now 2 versions of me, which is quite disturbing. So I suggest you all go and have a break now and get over that.
Coming back. Sorry, I'm gonna have to stop.
Hi everyone. Okay, so I pulled you back. I gave you much longer on that because primarily because I could see that you were all getting there actually and doing really well, and I didn't want to stop you too prematurely on this because for me this is the most important bit. You're actually building one of these models, and if you can do this, then if you're doing a discrete event simulation in your project, this is all you need to do. Basically, this is all the basics. You're actually putting together one of these models. So I wanted to spend a bit more time on this, and also because the next bit of the lecture is you going off to watch a couple of short videos anyway. So you'll just need to do that outside of the session. They're pretty short. They're about less than 15 minutes each. So hopefully quite easy to digest. But I would encourage you to check those out because it'll show you how to do some stuff. But I just wanted to give you a bit longer to work on this. So I'm going to pick on a couple of groups just to show you what they've done. I'm going to be a bit mean. And I'm going to manually pick on one group who I've just seen has got a working model. So I wanted to demonstrate. So Talkie Toaster, I'm afraid I'm going to pick on you guys first. And if somebody could talk through what you've done and show the model running, that would be great.
Yep, I will have to ask someone to jump in if in case I have a coughing fit because I'm ill, so sorry.
No problem.
Because of course having one cold isn't enough. This is the second one I've had in about 3 weeks. Okay, so can people see my screen?
Yep, is that fine?
Yep. Lovely. Okay, so nice and easy with the imports, just 3 that we normally use. In our class G, we did the inter-arrival times, the means, the probability we decided to add as a global variable in case we needed to change it later if we wanted to use it at another point. And then our resources are there as well, and the warm-up results period and the number of runs, although when we get to the end, you'll see we haven't actually done 100 runs yet because we didn't have time. In the patient class, we initialized all of the queues as the floats with the not numbers. And sorry. And also defined whether or not they were going to the ACU as false, so that then when we went on to do the probability of them going to the ACU, it would then change to true. And then we get on to the model itself, initializing. I won't go through all of this. I'm sure most of you have done something similar, defining everything as the resources, and then the Q means is 0. And then we created our data frame, which is very similar to the example, in that I pretty much copy and pasted and changed variable names. Excuse me. Then when we did the generating patients, we set the counter to add a new patient every time, as we've done before. Sorry, I think I'm going to have to ask one of my team members to jump in for a second.
Yeah, sure, no problem. I can understand that. Thank you for struggling through with that. Anybody else from Talkie Toaster that can just finish off the explanation on that one?
Yeah, I'm happy to jump in there. So can you hear me all right?
Yep, I hear you fine.
Great. So yeah, so we were on the generate patients line, I think there. So that we set up our new patient as an ED patient, gave them a new counter, and self-to-env process. Yes, that's then starting off the next method down below. Figured out or derived the inter-arrival time for them. Then yeah, carried on with the timeout. So when did that time end? When did they get freed up again? The attend-ED method then comes in. So what time did the next one start reception queue? Is when they started queuing. We requested the receptionist, and that flows through as it did before. So that's all the same as the last time we looked at these models. So I'm just going to try and pull out the differences between this approach and the previous approach for time. So then, so in fact, all of the attend-ED flows through as it did the previous week. So start triage queue, exactly the same as before. The difference is the logic on line 103. So if patient is ACU is equal true, which has been that goes back to our probability from before. Then we say, well, now you're going to start queuing for the ACU because your probability is such that you will go that way in the path. And that's then what follows is conceptually the same as every other stage in the process. So when did they start queuing for ACU? When did they end? What's the time they were queuing, which is the patient.queueACU equals line on 110. And how long were they?
So sorry, I'll be right back. There's someone at my door.
Okay. And then the else line is if their probability was such that they were false on the is ACU line, in which case they go to the ED to see the ED doctor. So just on line 117, Sally, and then with the self.ed doc request. So again, as before, requesting the resource, yielding the resource, and then working out how long the queue time was and how long they were with that resource to figure out what the sort of run time is now on line 126. And then we missed this initially, but the if statement on 128 is to account for the warm-up period. So it's saying if the time now is, so if the warm-up period is passed, if m.now is later than the warm-up period, which is defined in the G class, then add to the data frame the relevant details, the relevant patient ID and the various queue times that have been calculated. And then self.results.df, append that to the sort of main data frame. Line 137 is a method which then calculates the means for each of those queue times for the run that we're currently in. So for each patient in the current run is what's happening there. And then the method on line 143 is the run, the running of the model. So it's and that's the output from there is for print statements are for print statements. For each of those means for the queue times and the patients that have been generated for this particular run of the model. What we didn't get to is the for loop for the number of runs. So that would be the next stage in our work.
Fantastic, thank you very much. Yeah, really nice. And do you want to just start it running so just we can see the thing running as well? What I really liked as well about your model, I thought it was a great idea to have to cast the nans as floats from the start. So you're basically assuming that everything is not a number, and then you're just, unless it gets overwritten, which is a much more elegant way of dealing with it, because then your everything will work in pandas, and then you can just overwrite those not numbers with actual values if and when you get them, which is actually a really nice way of doing it. I like that. So yeah, so great. You've seen, obviously you've run the model, as anybody else that got that far as well should have found, that you will get very high numbers in terms of the weights for the assessment bits compared to the weights for the triage and the registration, which shouldn't be too surprising, because this is based on the very first question I asked you at the start of this course, where you had a massive bottleneck around sort of seeing the doctor, and also if you look at the numbers themselves, I mean, you compare the time for registration and triage to the time for ED assessment and ACU. But as Sally's demonstrating, you can then, beauty of this course, you can play around with it. So if you suddenly start adding in more doctors, you can see how those numbers go right down. And of course, that's exactly the sort of thing that you would do with this kind of model. So brilliant work, fantastic. I wanted to, so sorry for picking on you, and thank you, Sally, for struggling through with that. But I just wanted to show one of the groups that I knew had got a working model. So I am going to pick on one more group, and I'm going to spin the wheel for that. So let me just bring up the wheel of names, the much loved wheel of names, I should add. Oh, I forgot to remove Talkie Toast, so I'll spin it again if that comes up. So it looks like, it's going down to the wire. Oh, it's just gone into Max. Okay, so would someone from Max be happy just to talk through what they've done?
I'm happy to talk through it, but I haven't quite got it working.
That's fine.
Okay, let me just share my screen here. I think. Can you see that?
No, nothing's appeared.
What about now? Sorry, I don't think
Yeah.
Yeah. So I have, so there's a similar way of set up all of the use the classes or the global parameters here for all the various assessment times and nurses, doctors, etc. So I tried to keep all of the all of the kind of like stages into a single function that I've called a 10 stage. So you could then cut down on the amount of code instead of having the block to do the stage for the reception, stage for the triage and everything like that. You can just call this function multiple times because it's mostly the same. This may have been what's made it not work, because I'm probably doing lots of funny things with changing class instances and it doesn't like it.
That's a really nice idea. I like that. But yeah, that's probably why it's not working. One of the things that you have to be aware of when you do that is to do with the yield statement and the way that that passes control back to SimPy. So that might be causing complications, but it's worth looking at that because that might be if you can get that working, that'd be much more elegant. Sorry.
Yeah. So in the main process, I've got a self.env process, and each one I do in a 10 stage and then pass in the name of the stage here. And the way that I handle the kind of differences in each one is in the constructor, I've got a stage resource dictionary, and this has each of the stages says what the resource is, in this case, the receptionist or the nurse or the ED doctor, the ACU doctor, and then gives the time in here, so that when you're calling it, the patient arrives, they get their ID, and then you start the activity generator and you go into the reception stage to start with. That just calls this function. It checks that the stage is valid. It gets the right resource. So in this case, it uses that dictionary I did before to get, if it's the reception, to get the receptionist or to get the ED doctor or the nurse. Then goes through and does the normal stuff, calculates the queue, adds the queue time to the patient. And I know it's doing this right, but yeah, it doesn't seem to be, it gets the queue time right here, but it doesn't seem to save it. So it changes the instance, but then it just gets rid of it further down the line, which is a bit confusing. I can't quite figure out why that is. But then, yeah, as before, does the timeout and does the waiting time. It does that for all. It does that for all of the stages. So it goes through reception, triage. I like the idea of putting that in the as an attribute of the patient. I should have done that, and then decides whether it's going to keep the warm-up data. So it just checks the end time if that's within the warm-up, and then adds to the data frame all the times. But this is the error I'm getting. You can see down here, it gets the right time, but then it's just overwritten. It's just taken all the default values. So obviously I've got to have a little bit of a think of how I'm passing this class instance around, because it's not very happy about that. But yeah, that's as far as I go.
That's really nice. I suspect it's probably just something very simple I definitely keep having a look at that, because I really like that. It's a really nice solution that you're coming up with there. And what I like about that as well is that so I mentioned this to a couple of the groups. So obviously a lot of the times when you're building these kind of models, you're very often first of all trying to work out where your bottleneck is. So you're saying, given this amount of activity and this is the resource we've got, where are the queues building up? That's usually almost always the first question you'll answer with that. And then very often it's, well, what can we do about it? Well, we could speed up that bit of the process there, or we could put some extra resource there, take some, what happens if we take some resource off there? But sometimes what the question is, well, what if we did that step before that step? Or what if we remove that step entirely and we sort of juggle things around? So you don't tend to do that as often, but sometimes it's more a question about the structure of the pathway. And obviously the way you're approaching that there, that would be a much easier way of doing that, because then you could essentially just move around bits of the pathway, the order in which things happen, and remove things entirely, and you could very elegantly do that. So I like that. So yeah, it'd definitely be worth pursuing that and seeing if you can get that working. And if you do, please do share that, because I think that's a really nice solution if you can get that working. I think I tried doing something similar once years ago and fell into the trap that there's complications because of the way that SimPy deals with the handling underneath. But I don't think that's the problem you're getting. I think it's probably something simpler. So hopefully that you can get that working. That'd be great.
Okay, I'll try and figure that out. Thanks, Dan.
Yeah, brilliant. Thank you. Fantastic. Okay, I'll stop there because it's time for lunch. I will put up the solution for you as well, as always, so you can check it against the solution. But if you didn't quite manage to finish off, do have a go at finishing that off if you get a chance as well. And do look at the video. So in your lecture notes, on the very final slide, I've put two little lectures. They're tiny, as I say, they're less than 15 minutes each, and they'll just take you through some examples of how you do priority-based queuing, so how you prioritize people in a queue rather than just first in, first out, and also how you model resource unavailability. So definitely check those things out. They're only very short, and it'll guide you through. One note on that, because they're from recordings from last year before I was using F strings, you'll see that I'm not using F strings in the videos, but in the materials that I've provided, so I've given you the code that goes with that. I've changed that to F strings. I just didn't want to record 30 minutes of perfectly good video just because I didn't use F strings. So do check those things out. Otherwise, I will see you in an hour. This afternoon's going to be a bit different. So this morning was quite technical, and I have to say you've all done a fantastic job. It's brilliant to see how much you've come on and able to build these models. This afternoon, we're going to be doing something a bit more creative and a little bit different in terms of cellular automata and getting those creative juices flowing, and something a bit different, a bit more abstract. So hopefully this will generate some interesting ideas this afternoon, and not so much on the technical heavy side. So feel free to stay on the call. If you do stay on the call, just please make sure you're muted, otherwise I randomly get things booming out from my speakers, as does everyone else. But otherwise I will see you at 1:30. Okay, have fun everyone. Okay, very good afternoon, everyone. Hope you had a nice break over lunch, and hope you enjoyed this morning's session around discrete event simulation. Apologies if you can hear any strimming going on. The gardeners outside. For a few moments I was slightly panicked because I didn't realise it was outside and thought that my PC was about to blow up. Just heard this very odd noise coming from that direction, but fortunately it's not, or at least I hope it's not. So this afternoon we're going to talk about the start of our journey through modelling behaviour, and this is an interesting one, I think. So my PhD was actually in behavioural modelling, specifically ecological behavioural modelling, where I looked at using agent-based simulation. And agent-based simulation is going to be the core of what we're going to be talking about in this particular module. But in order to introduce that, I'm going to start in this session by talking about cellular automata, which is kind of the purest distilled form of agent-based simulation. And this session is going to be a little bit more abstract, and it's going to require you to think in a little bit of a different way about the ways in which you might capture aspects of behavior and put those into a model. And I should also, I think I mentioned the other day, we've never actually had a sort of behavioral model, agent-based simulation model as part of HSMA, and it'd be fantastic to see one. So if any of you do come up with some ideas for how developing behavioral models, I'd love to see them. I think there's a lot of scope in it, and indeed this afternoon you'll get a bit of a chance to start having a think about that as well. So far we've kind of talked about approaches like we did this morning, such as discrete event simulation, which is all focused on the processes within a system. But sometimes there are behavioral aspects within a system that are important. So most of the systems we model in discrete event simulations will have a behavioral aspect to them, but where that behavior is important, or indeed maybe even the focus of what we're trying to capture and what we're trying to intervene with, then sometimes some of these other methods, such as agent-based simulation, cellular automata, can actually be really useful. And so in this module, we're going to look at ways in which we can capture model behavior, as I say, predominantly using agent-based simulation. But this is a kind of intro to that, using cellular automata. That's the plural, singular being a cellular automaton. The advantage of doing this is that it introduces a lot of the core concepts behind agent-based simulation. So this is a slightly more abstracted approach, cellular automata. When we come on to the agent-based stuff within the second and third sessions of this module, you'll actually get to try something out in terms of something very, very real. In terms of specifically, you'll get to model a disease pandemic, for example, using this kind of thing. So let's talk about cellular automata. So there are certain core components of cellular automata. They are basically made up of an n-dimensional grid of cells. Now, typically, most cellular automata are either one-dimensional or two-dimensional. You can have more than two-dimensional cellular automata, but in most cases, the sort of things you'll see will be either one or two-dimensional. So basically, you've got this grid of cells, and it may be just a one-dimensional grid, but it's a grid nonetheless. And each cell is in one of a number of different states. And within a cellular automaton, time advances in time steps, much as you're used to seeing with discrete event simulation, but the time steps in a cellular automaton are referred to as generations. And the reasons behind that will become clear as we start to explore this. The states of each cell may change in each generation according to certain rules that are specified. And the rules that determine the state of a cell in any given generation will typically depend on the state of that particular cell in a previous generation, and or the states of the cells around it, which we refer to as the neighborhood. So basically, you've got lots of cells. Each of those cells is in one of many different states. Time advances in generations, and the states of those cells will change between generations, and that's typically dependent on what state a particular cell is in one generation, and also what states its neighbors are in, the cells that surround it. Okay, so all this will become much clearer as we look at some examples. So why should we use cellular automata? And when I started my PhD many moons ago, I looked into kind of cellular automata initially, and it's a really fascinating area. It's kind of magical, because when we look around, there are lots of things in the natural world, natural phenomena, that actually can't be explained using conventional mathematics. So things like the way in which a snowflake is formed, or the patterns that we see on a seashell, conventional mathematics can't actually explain those things. And that's interesting in itself. And we can also see certain phenomena within our human world, in human systems, that things like the formation of traffic jams or the spread of crime, that this approach of using cellular automata can actually help explain where conventional mathematics can't. So you can develop a cellular automata that will show you how a snowflake forms or how a pattern on a seashell forms, and I'll show you quite a stark example of that in a moment. And it's because of the slightly different way in which cellular automata works compared to conventional mathematics. So cellular automata, these kind of phenomena that cellular automata can explain, these things arise emergently. They're essentially the product of very simple individual rules that are consistently applied, but which lead to these very complex seeming emergent dynamics or behaviors. So the way in which a snowflake forms is dependent on very, very simple rules at a very small scale that then create these very wonderful, beautiful, and apparently quite complex patterns at a large scale. So in ecological modeling, which, as I say, was sort of my background for my PhD, this kind of approach is actually quite well used. And the reason it's so well used is because very often when we're modeling animal behavior, we know very often we know a lot about how individual animals behave. Certainly in terms of their motivations, and we can consider certain rules of thumb that we could apply to individuals, but we often know much less about how those dynamics interplay and work at a sort of population scale. So, for example, we might know, and this was kind of the starting point for my work, that an animal was a very efficient forager that needs to fill up with resource as quickly as possible. So, for example, a bumblebee. So my research was all about bumblebee foraging, basically, and trying to model the way in which bumblebees forage. And we know that basically they have to fill up with food as quickly as possible. And so that will drive the kind of decisions that they need to make. But we often know less about what happens at a population level, i.e. with bumblebees at the kind of colony level. So with these kind of approaches, we can code in the kind of individual level rules of thumb, the simple rules that we can apply, and then see what happens as all of those individuals who are following these individual simple rules interact with the environment and interact with each other, and what kind of emergent behavior emerges. And just to say a note, you may also come across this, particularly if you're looking at anything in ecology. Agent-based simulations, often referred to as individual-based modeling, or IBM. So you'll sometimes see references to IBM, individual-based modeling, rather than ABS, agent-based simulation. They're used interchangeably. It's exactly the same thing, but individual-based modeling is much more widely used within the ecological circles. But such applications aren't just limited to ecology, and clearly there's real benefits and real value in applying these methods in an ecological context. But we can also think about human systems as well. So, for example, we might be able to model rules that represent the behaviors of individuals, their own motivations, the interactions of humans in a system, and we may want to understand what the kind of emergent dynamics look like at the population level. So can anyone think of a very topical example that would fit that?
I guess maybe if a patient's deciding whether to go to a GP or ring 111 or go to ED.
Yeah, that certainly would be something that you may want to consider capturing via a behavior model. I think probably the big one is COVID, and actually that kind of pandemic disease spread model, where you're looking at the way in which people are behaving, the way in which they're interacting, can actually be captured very well by this. And in fact, a lot of disease models historically have used agent-based simulation approaches. because it models the way in which people move and interact with each other. And of course, those are key concepts when we're thinking about the way in which a disease will spread. So let's look at an example of what a cellular automaton might look like, because I realize it can be a bit difficult to get your head around just in terms of words. So let's visualize something and hopefully make this a little bit more real. So let's imagine a two-dimensional cellular automaton, so a two-dimensional grid of cells. And each of those cells is in this case, in our automaton here, in one of three states, is either off, which is white, blue, or it's in the green state. And let's imagine we've got some rules that say, one, if the cell is off in a generation, and there are green and or blue cells present in its neighbors, then switch that cell that was off to on, either as a blue cell or a green cell, depending on which cells are most prevalent in their neighborhood, breaking ties randomly. And then we've just got a second rule here that says if the cell is blue or green in that particular generation, then switch it off in the next generation. So those two very, very simple rules. It basically just says if you're blue or green, then you'll be off in the next generation. If you're off now, then if there are blue or green cells around you, then switch on in the next generation, and whichever you're surrounded most by, switch on to that color. And if you're surrounded by an equal number of blue and green, then just pick one of them at random. Okay, so really, really simple rules, but that's the kind of rule that a cellular automaton would run by. And the neighborhood here, we're using something called the Moore neighborhood. I'll talk more about different neighborhood types in a bit. But that basically means that you've got a cell, and a Moore neighborhood basically means the 8 cells surrounding it plus the cell itself. So the neighbors are the 8 cells that surround it. So up, down, left, right, plus all the diagonals as well. And that's a fairly common neighborhood that's used within cellular automata. So given our cellular automaton that we've just made up here, what will happen to each of these cells in the next generation? So what's going to happen to cell A in the next generation?
Blue.
Yep, that one's going to turn to blue because it's got within its neighborhood here, we've got 3 cells and we've got a blue cell here, and there's no green cell, so that's going to switch to a blue cell. What about B down here?
Blue.
No, so B will actually stay switched off because we've only got these neighboring cells immediately around it here, and there's nothing that's blue or green, so that one will remain switched off. Neither of these rules essentially will kick in. What about C here?
Turned off.
Did you say turned off? Sorry.
Yeah, 50%.
Yeah.
Yeah, that's right, because it's rule 2 will kick in, saying that if it's blue or green, then it'll switch off next time. D.
50% probability of becoming green, and
Yep.
25% probability of blue, and another 20. Well, yeah, and
So,
another 50 or so percent of staying off.
So this one will actually just turn green because rule 1 will kick in, which will say, so basically in the neighborhood of D, we've got 2 greens and a blue. And rule 1 tells us that if there are blue and or green cells are in the neighborhood, which there are, then switch this cell on to either blue or green, depending on which cells are most prevalent. So there's more green than blue, so this will become green next time, essentially. And then E.
Green.
It could be green or blue. So in this case, we've got 2 cells that are switched on in the neighborhood. We've got a green and a blue, which means we're tied. So we're going to break ties randomly. So one of those will be randomly selected as the color for the next generation. Okay, so I mean, obviously this is just a cellular automaton that I've completely made up, but it's just to give you an idea about how these kinds of things work and the kinds of rules that you use and how they evolve over time. And so obviously then once those cells had all changed, then in the next generation after that, there would be a further evolution depending on the cell configuration at that point. So I mentioned that cellular automata can be multidimensional beyond 2 dimensions, but that most are either one-dimensional or two-dimensional. So in a two-dimensional cellular automata, we've got a 2D grid of cells, but in a one-dimensional cellular automaton, we have a single row of cells because it's only one-dimensional, but we typically visualize that in 2 dimensions by showing the evolution of that automaton over time using the y-axis. So essentially we have, just imagine if here, a one-dimensional cellular automaton would just be, say, one of these rows, but we would visualize it in 2 dimensions by saying, this is the first generation, and then this is what it looks like in the second generation, and this is what it looks like in the third generation, etc. So we get that 2-dimensional visualization that shows how the one-dimensional automaton would evolve over time. Now, I'll show you a bit. I'm going to show you some one-dimensional cellular automata in a bit, but there's a special type of one-dimensional cellular automata in which there are 2 possible states. So it's a binary system. You've just got 2 states, 0 and 1. And this is known as an elementary cellular automaton, where you've got 2 states, and the state of each cell in the next generation depends only on whatever state it's in itself and its 2 immediate neighbors. So elementary cellular automaton, one-dimensional. It's in each cell is in one of 2 states, 0 or 1, and whatever state. So if this is our cell of interest here, cell C, what state it's going to be in the next generation will depend solely on what state it's in now and the state of its 2 immediate neighbors here, N1 and N2. Now, if each cellular automaton has a unique rule set, then that means there are 256 possible elementary cellular automata. And the reason there are 256, if we think this through, so there are basically 8 possible state configurations for a given cell and its immediate neighbors. So if we were to write them in terms of their states, so remember the states of the cells are 0 or 1, then one possible set of 3 would be 1, 0, 1. So imagine them on and off, on, off, on. They could be all on, they could be all ones, they could be 001, etc. There are 8 combinations of those because there are 2 valid states for each of 3 cells. And each of those 8 configurations will output either a 0 or 1 for the cell in question for its evolution into the next generation. So a unique rule set will specify whether each of those 8 configurations outputs a 0 or a 1, which gives us 2 to the power of 8 possible rule sets, which is 256, where each rule set can be specified by what's known as an 8-bit array, which is an array of 8 binary values. Don't worry too much about the maths, just know that that's why there are 256 of them. Now, Stephen Wolfram, who was a big name in cellular automata and agent-based simulation, he was a computer scientist very famed for his research into cellular automata, particularly in the 80s, and proposed something called the Wolfram Code, in which each rule set of these elementary cellular automata is allocated a number between 0 and 255. We've already established there are 256 possible rule sets. What's really interesting, though, the interesting bit, is that some of those rule sets have been shown to have really special properties, such as generating really complex emergent behavior. And one of them, rule 110, rule set 110, has been shown to be capable of something known as universal computation. Now, again, I'm not going to go into the details of all this. The key thing I want you to take away from this is that if we look back, these are incredibly simple rules. Okay, all we're saying with an elementary cellular automaton is that you've got some rules that define a one-dimensional cellular automaton, and the future of a cell in the next generation will depend only on what state it's in now and what state its 2 immediate neighbors are in. That's it. So the level of complexity that you can get to is very small. okay, there will be a certain number of combinations, and that will result in either this cell being a 1 or a 0 in the next combination. And there are 256 possible elementary cellular automaton based on all those different combinations. That's it. So there's really simple rules. Okay, we could write a rule now that, but it would have to fall into one of those 256. But out of that stuff, just from that really simple rules, that's all we're doing, you get this really special, complicated behavior that emerges. Okay, so let's have a look at a one-dimensional elementary cellular automaton simulator. And I've put all these links in your notes, so you can check these out yourself. And indeed, in the exercises, I'm going to get you to have a little look at some of this. I'm first of all going to just come out of that. Let's click on that link. So I'm going to show you rule 110 first of all. So I'll click on that. So this is rule 110. Now I can specify the different rules. Remember, there's 256. I can go from 0 to 255, and I can also specify the grid size in terms of the number of cells. Remember, it's one-dimensional, so we're only specifying essentially a width here. Could be a height, but we typically represent them as along the x-axis, and then evolving along the y-axis. So let me just to make it more interesting, we'll have 100 of them, and I'll start with a single cell. Let's see what happens. Now, that's really interesting. Something here. Remember, we've just got some really simple rules that are governing this. We've got these weird patterns that are starting to emerge. Now, that's really odd in itself, because all we've done is specified, as we've seen, we are limited in terms of the complexity of the rules that we can put in. Any cell is only, its future is only determined in the next generation by what state it's in now, and the state of its two immediate neighbors. And you can see the 8 possible combinations for this particular rule set. Okay, so for rule set 110, if the cell is on and its two immediate neighbors are on, it'll be off next time. If it's on and the one to the right is on, but the one to the left is off, it'll be on next time. That's all this means. It just shows you what those different rules do. Those 8 really simple rules generate that. Now that's quite weird in itself. And as I say, it's capable of all these fantastic things in computational theory, which I absolutely don't want to go into, but know that these things have special properties. I'm also going to show you rule 30, which has been used for random number generation and also for cryptography. So let's go to rule 30. Again, I'll put on this, and let's clear that, and I'll start with a single cell again, and then run it to the end. Now, this is even more interesting. Again, we've got this, we've got a different pattern that's emerged this time. But what we've got here is kind of a little bit between order and chaos. So we've got these interesting little shapes that are emerging every now and then, but then also this sort of pattern that's running underneath this. And in fact, if I increase the resolution of that a bit, let's put in 1,000 cells and single cell, and then run to end. Oh, that's probably going to be too small. I shouldn't have done that. Let's take that down to about 5. Let's take it down to about 200. I think would be better. My computer really is now complaining. There we go. That's better. So we can start to see this. There's something really weird happening here. Okay. Remember, again, very simple rules. These are the 8 rules for that rule set that determine what should happen to a cell in the next generation. But we've got something really complex emerging. If you didn't know anything about how that was emerging, and somebody just showed you that and said, how was that formed? You'd imagine there were some complex rules that were governing this. And in fact, they're not. It's just these 8 very simple rules applied at a cellular level to each cell for each generation, just builds up and builds up until you get this really interesting pattern emerge. What's even weirder, I think, is that so rule 30, the one I've just shown you, is an example of something known as a chaotic cellular automaton. So it's one in which that produces this complex, seemingly random patterns, though from these really simple, well-defined rules. So we saw those sort of triangles appearing apparently at random, just this randomness within this ordered pattern in the background. Now, I think this is really weird. So you remember that pattern. In fact, let's just scroll back to it. Here we are. This is the shell of the cone-snail Kronos textile, which has that pattern on it. Now, that's really odd in itself, and is again goes back to this point that there are lots of things in nature that conventional mathematics can't explain, but which cellular automata, or the principles of cellular automata, in terms of just having very simple rules that are applied at a cellular level that then build up and build up, seem to be able to demonstrate these completely random things in nature that don't seem to be explained in any other way. And there's lots of examples of this kind of stuff within cellular automata. Okay, so we've talked about elementary cellular automata as an example of a one-dimensional type of cellular automata. Let's now imagine a different, a more generic one-dimensional cellular automaton. And that cellular automaton has a number of states, one of which will represent a dead state, and the rest will be different states of being alive. So a little bit like the one, the 2D one I showed you that I made up, where you've got an off state and then various different alive states. So let's just generically imagine a one-dimensional cellular automaton that has that. You've got one state that's dead and then different alive states, and you've got a neighborhood of a given size. Okay, so let's imagine that this cellular automaton that this sort of theoretical automaton that we're imagining has a rule that says if a cell and its neighbors are dead, then the cell can't come back to life in the next generation. So if it's dead and there's nothing alive around it, it'll remain dead. Okay, that's easy. But beyond that, for all of the other rules that will essentially generate potential life, we're going to randomly generate all of the other rules. And we're going to have a parameter called lambda that we can adjust. And lambda will basically represent the probability that one of these randomly generated rules will lead to an alive state as opposed to a dead state. Okay, so basically what that means is you've got one fixed rule that says it remains dead. If it's dead and there's nothing alive around it, then it remains dead. But all of the other rules will randomly generate. And we'll have a parameter called lambda that we adjust. And as lambda tends towards 0, so the closer it gets to 0, then more of the rules will lead to death rather than to life. So you will have more cells dying quickly, because most of the cells that will be, most of the rules that will be randomly generated will result in the cell being dead in the next generation rather than alive. But as lambda tends towards 1, then we'll have more cells that continue living because most of the rules will lead to life. So if we go back to this here, so obviously this is just an example of an elementary cellular automaton, but if we imagine this as our example, we're essentially going to randomly generate these rules. And remember, it can be for a neighborhood of any size, because we're now thinking generically. But what we're saying is we have a lambda parameter, and if the lower that is, the more of these will lead to the cell being dead in the next generation. And the higher the lambda, the closer it is to 1, the more of these rules will lead to life, one of the live states. Remember, it won't just be binary, we can have more than one life state in this theoretical example. Now, there's an abstract concept known as the edge of chaos, which is a fantastic name, I think, which basically describes the points that lie between order and disorder or chaos. And what it says is when you're in the edge of chaos, there's huge amounts of instability because you've got this constant interplay between order and disorder or chaos. And I'm going to show you this and you'll see what I mean. So if we think about in terms of cellular automata, computer scientist who's named Christopher Langton did a lot of experiments into the concept of the edge of chaos using one-dimensional cellular automata. And what he found, there's kind of this transitional period in complexity in this emergent behavior in a one-dimensional cellular automata that sits between the move from these patterns that emerge. So we've just seen a couple of example patterns. You get the one end of the scale, you've got the patterns that are uninteresting because they're highly ordered. There's just a very high structure to it. They're very highly structured, very highly ordered. And then at the other end of the scale, you've got stuff that's not interesting because it's too chaotic. It's just, there's no order whatsoever. And he was the one that put forward the idea of using lambda to try and explore the space between those two things and find this edge of chaos where you've got cellular automata that essentially generate these rules that generate this emergent behavior where there's this constant interplay between order and disorder, and that's known as the edge of chaos. And it turns out that's quite important because cellular automata that are in the edge of chaos can be used for universal computation. So from a mathematical computational perspective, it's actually really important. So you're probably thinking that all sounds very weird. Let me show you, because nothing's more powerful than seeing this in action. So on this link, you can actually explore the edge of chaos yourself. And there's some example ones where you can see some different examples of where the, rather than having a randomly generated example, it'll have some sort of pre-programmed ones which show you various different things. But I'm just going to go into the main bit here. Okay, so I'm going to start off. So this is essentially our slider for lambda. So you can see lambda here is very low. If I go over to the right, it'll be very high. So when I go very low, obviously that means that cells are, more of the randomly generated rules are leading to death. Okay, so when you're down this way, there's not much happening because things are dying out really quickly, because most of the rules that are being randomly generated lead to a cell dying in the next generation. If I go right up to the other end of the spectrum, we get stuff like this. Now, most of the rules are leading to cells being alive in the next generation. And there's kind of a chaos in it, but it's just a chaos. It's almost meaningless. And in fact, if we go sort of right up, you can see that it becomes somehow uninteresting because of that. But somewhere around the middle, as we start to reduce lambda and start to get this interpoint here between the two, we start to find weird stuff happening. So again, we're still a little bit too ordered there, but if we start, here we go. Now we're entering the edge of chaos. So we've got this constant interplay here between these little chaotic bits here, and then this ordered structure happening here, and then all of a sudden these weird sort of chaotic bits that happen down here. And it's this constant interplay, and there's some very, very strange stuff that's going on in these particular rules. And you'll suddenly have, you think a pattern's remaining stable, and then suddenly something like that will happen, and everything will be thrown off again. And it's this, where we are now, is in what we call the edge of chaos, where you've kind of got this interplay between things that are too dull because they're too ordered, or they just die out too quickly, versus the things that are too dull because it's just a mess of chaos. And so this is, turns out this is a really important area for computational theory, because these sort of rules that generate this are actually incredibly powerful in terms of what they're able to do. Let me just pause that. Makes a nice screensaver, I think. Okay, let's go back to thinking a little bit about two-dimensional cellular automata again. So two-dimensional cellular automata share the same principles as one-dimensional cellular automata, but obviously there are greater possibilities in terms of your neighborhood configurations, because in a one-dimensional automata, with an elementary one-dimensional automata, then you're just looking at the two immediate neighboring cells. And even in more complex one-dimensional cellular automata, it's basically just how far out from that cell you go. But obviously, when you bring in 2 dimensions, you've got more potential complexity. Having said that, there are 2 very commonly used neighborhoods in 2D cellular automata, and these are the 2 that you'll see most of the time. So there's this one here, which is known as the von Neumann neighborhood, in which basically the neighbors are north, south, east, and west. So it's up, down, left, and right. The neighborhood includes the cell, but the neighbors are these 4 here. and then the more neighborhood, which I introduced earlier, which is basically the same, but also includes the diagonals. Okay, so von Neumann and more are two very common neighbors that you'll see. And when you get to practice, when we come on to actually coding some agent-based simulation for disease spread in the following sessions, you'll see how you use these different neighborhoods and how you tell a Mesa, which is the package we use, what sort of neighborhood you want to use. Now, it's quite possible at least some of you may have heard of this cellular automaton, because it's quite famous. You may not have, but certainly when people think of cellular automata, this is the one, if they know anything about it, this is the one they tend to think of. And this automaton is known as John Conway's game of life, very commonly also referred to simply as life, and it was devised by the mathematician John Conway. Now, life is a 2D cellular automaton in which each cell can be in one of two states, alive or dead. So back to sort of binary states. You're either alive or you're dead. Very simple. And it uses a Moore neighborhood, which if you go back, we can see that's basically the all 8 surrounding cells. So the up, down, left, right, plus the diagonals. And the game of life, or life, consists of 4 very simple rules. The first rule: if a cell is alive in one generation and it has fewer than 2 alive neighbors, then the cell will die in the next generation. And that's designed to model underpopulation. Okay, so it's underpopulated and it dies out. If a cell is alive in one generation and it has either 2 or 3 alive neighbors, then it will live on in the next generation. That's kind of a stable state. If it's alive in one generation and there's more than 3 alive neighbors, then it will die in the next generation through overpopulation. So it needs 2 or 3 neighbors basically to survive. If there's fewer than 2, then it dies because of underpopulation. And if there's more than 3, then it will die through overpopulation. Now, if those are the 3 cells, the 3 rules if a cell is alive. If the cell is dead and has exactly 3 alive neighbors, then it will be born, become alive in the next generation, and that emulates reproduction. Okay, so if none of those apply, then that means that the cell is dead and it doesn't have exactly 3 alive neighbors, so it will remain dead. So 4 very simple rules. Okay, if it's alive, it's got less than 2 neighbors, you die. If you've got 2 or 3 neighbors, you survive. You've got more than 3 neighbors, you die. And if you're dead, but you've got exactly 3 neighbors who are alive, then you'll become born in the next generation. 4 very, very simple rules. Okay, we can imagine working that out on paper. Indeed, you get to practice it now. So given those 4 rules, what's going to happen to these cells in the next generation? So what will happen to cell A? Say it again, sorry.
It will die on the next generation. It doesn't have any neighbors.
That's right. It's going to die through underpopulation. Cell B?
Going to die through overpopulation.
That's right. Yep, it's too crowded, cell B. What about cell C?
Live on.
Yep, so that one's going to survive. That one's got exactly the right number of neighbors, so it's in a nice stable position. What about cell D? Yeah, that's right. It's going to be born because it's dead, but it's got exactly 3 alive neighbors. So that's going to be born as a new life form in the next generation. And then E? So E will remain dead because none of these rules essentially will apply. That it's already dead and it can only come back to life. It can only be born if it has exactly 3 neighbors, and obviously this one's got 4, so that one will remain dead. But we can see that there are very, very simple rules essentially, and we can just sit down and work them out. So we see that you just got these 4 very, very simple rules, but what's really interesting about the game of life, as with many cellular automata, is that out of those very, very simple rules, we find this very complex behavior that emerges. And what's particularly interesting is that we find in the game of life, there are certain kind of life forms that emerge, these patterns, which are referred to as life forms. And there are 3 different categories of these life forms. And I'll talk more about those in a moment. But there are things called still lifes, which are basically life forms that just remain stable, they don't change. There are things called oscillators, which basically repeat after a certain number of generations. And there are things called spaceships, which are patterns that move themselves across the grid. But before we look into that, let's have a little look at some of this stuff so you can see what I mean. So remember, don't forget there are 4 very, very simple rules that are governing this. At no point have we told it anything about creating any life forms. Okay, let's see what happens. So if I go into here now, I've just drawn a little pattern here. This isn't entirely at random because I've already generated this pattern before. So I've got my cells, my yellow cells here are alive and grey cells are dead. And I'm going to apply the game of life to this just using those 4 simple rules. Let's see what happens. Now, we can see some really interesting stuff that's starting to emerge. We've got this little life form up here that's drifting off northwest. We had a little bit of evolution going on down here. And then we've got this little life form that's been left alone here, just blinking between 2 little patterns. Now that's really weird. All we've done is set up a very simple grid of cells here and applied 4 very simple rules, and we've got this weird behavior emerging from it. Let's also have a look over here. We can have a look at some of the stuff that actually emerges out of this. And on this website, you can actually click on the different types of shape, different life forms, and it'll show you these things. And you've got all sorts of things here. We've got shooters with the spaceships that are bouncing back and forth and shooting out little life forms. This is crazy. You've got 4 very simple rules that are just governing what's happening to cells, whether they're alive or dead. 4 very simple rules, and this is happening. Now that's really odd. Okay, have a look at a glider. So that's a glider drifting as we just had a glider drifting. Let's just do a random one. We've got all sorts of weird stuff happening here, and little life forms that are being born, life forms that are being consumed. 2-gun one's quite good. I think that's the one we just looked at. All sorts of things. I'll let you have a little play around with that, but there's some really fascinating stuff. And this little option up here where it says toroidal world, that basically just means that when you get to the edge of the grid, it appears on the other side. Let's go to that one. You can also on this one here, you can click on the lexicon and it'll show you different patterns, and you can look at these different patterns. So if I want to look at what a demonoid looks like, then it'll explain what a demonoid is and when it was found and how it was named, etc. So let's talk a little bit about those 3 categories of life forms. So there's first of all these still lifes. So a still life pattern doesn't change from one generation to the next. It comes into being, but it then remains stable. It doesn't change in any way. And some common still life patterns that you'll see when you experiment with this is the block, the beehive, and the loaf. And those are 3 that you'll quite often see. There's many more, but those are 3 of the very common ones. And if you take a moment to think about this and why they're not changing, we can see why they're not changing. If we look at the rules, okay, so we've got this cell here that's alive. It has exactly 3 neighbors, therefore it remains alive. This one has exactly 3 neighbors, this one, etc. So all of those are remaining alive, but none of the surrounding cells that are dead have got exactly 3 neighbors, and so therefore they can't be born. And so we can see why it is when we start interrogating the rules. But at no point have we set up rules that we could have envisaged would have created this kind of behavior. Then we've got oscillators. So oscillators are basically patterns. We just saw an example of an oscillator called a blinker that repeats after a certain number of generations, which we refer to as the period. So this blinker is one that switches between a sort of horizontal bar and a vertical bar here. That's got a period of 2, which means it repeats after 2 generations. So it moves from that to that and then repeats. And this one, which you'll quite often see as well, got a pulsar. That one's got a period of 3. So it moves from this state to that state to that state, and then reverts back to that original state. So it will constantly keep cycling around. And then we've got spaceships. So again, we saw an example of a glider, which is one of the most common spaceships that you'll see. And basically a spaceship is a pattern that moves itself across the grid by a pattern that repeats after a certain period, but in a different location. So you can think of those a little bit like oscillators, these ones, but one in which they sort of move as well, a move location. And as I say, the glider is one of the most common types of spaceship you see, but there are others. So what's the period of this particular spaceship? That's a very odd sentence to say.
5.
Close. It's actually 4. So it's the number of different patterns before it repeats. So in this case, you've got this is the starting pattern, or obviously it could start at any of these, but let's imagine that's the starting pattern, and then it moves to this, then to this, then to this. So then it then repeats. It's in a different location. It's moved down slightly, but it is down to the right, but it has repeated. So it's got a period of 4. There's also these wonderful things called eaters. So eaters are still life patterns. Remember, those are the ones that are stable, they don't move, but which interact with certain other patterns without suffering damage. So basically, it looks like the eater has consumed the other life form whilst retaining its own integrity. I know this is all very weird, but let's have a little look at an example of that, because this is really, really odd to watch. So again, exactly the same rules. This is an example of an eater. So here we've got a glider, which we've been used to seeing. We know that's a glider shape now. All of the rest of these cells here form an eater. So this is a stable shape, all of this, apart from that glider. Let's see what happens as the glider moves into the eater. There we go. And it's gone back to its original state, but the glider has been consumed. The glider is no more. It's been eaten by our eater. Now that's crazy when you consider it's still those 4 simple rules. That's all that's governed this. And yet we've got this weird behavior where we've now apparently given birth to life forms that eat spaceships. Now, you couldn't have imagined that, I guarantee you, when I first started talking about 4 simple rules for cells being on or off. But that's what we've ended up with. It's weird, very bizarre. And these kind of patterns continue to be discovered within the game of life. In fact, there's an annual contest called the Pattern of the Year contest, in which people submit interesting patterns they've discovered, and they get judged. I mean, it really is a contest for everything, and fascinating thing. But if you want to find out more, you can look at previous entries as well, maybe even submit your own. If you follow that link, you can look at the John Conway's Game of Life Pattern of the Year contest. So you're probably thinking, well, this is all very fascinating, Dan. Thank you for showing us a life form that you've created that eats a spaceship. What's this got to do with me? Why are you telling us this? Well, a couple of reasons why I'm telling you this. First of all, it's to show you this concept of patterns, because patterns demonstrate this concept of emergent and also self-organizing behavior at a population level that emerges just from very, very simple rules at the individual level. And they also demonstrate that how these order can emerge from apparent chaos. So things can become ordered. We can create these stable life forms that emerge from apparent chaos. And then as we start to think about how some of this stuff might be useful, if we were to think about using a cellular automaton to represent a real world system, and think about how the rules that we apply could be used to emulate something that's happening in the real world, then these patterns that emerge can help us to understand that emergent behavior, why it's emerging, how it's emerging, and therefore how we might either encourage or combat it, depending on whether it's a positive or a negative thing that's happening. So it's a little bit more abstract in terms of the way we think. But if we think about these kind of structures and why these things emerge, and then think about how we would design a cellular automaton to represent a real world system, those kinds of complex emergent behaviors arising from very, very simple rules show us how we can get some really interesting insight, potentially, if this is representing a real world system, into how we might want to tackle something. Okay. So what I'm going to do now is I'm going to kind of hand over to you. I'll take a little bit of a break. And then for the next 80 minutes, I want you to work in your groups. And the first thing I want you to do is have a bit of a play. I want you to play with some of the stuff that I've just shown you using the link. So have a play with the 1D elementary CA simulator here. So that's the one where you've got the 256 different rules and looking at the different things, and also look at the edge of chaos phenomenon, have a little play around with that. And then have a little look at the game of life stuff. So there's two different, there's many different links, but two good ones here that I just showed you. See what patterns you can get to emerge from the game of life, and also explore some of the predetermined ones. So I showed you the lexicon button in this first one, or you can follow the different pattern buttons in the second link, and it'll show you some different patterns and some predefined patterns that you can use to see some of these life forms emerge. Also check out this link, which has got some other 2D cellular automata. So we've talked about the game of life here, which is the most famous, but there are others, and they're all brilliantly named. There's a 2D cellular automaton called Star Wars. There's one called Brian's Brain. This links to quite a few of those different ones, and obviously they'll all have their own types of rules and their own different states. And see what sort of things come out of those. So have a good little play around as a group with that sort of stuff. The reason I want you to do that is because I want you to start thinking and getting some ideas flowing for this bit. Because what I want you to spend then most of the time doing as a group is coming up with a design for a cellular automaton that could represent a real world problem. So I want you to start by thinking, having a chat about, some potential application areas where you think this sort of stuff could help. So this is a bit more challenging because this, as you can see, is a bit more of an abstract approach. But there are areas where this stuff has been used for very, very important things in the real world. And I gave you a couple of examples, things like, road traffic management and the spread of crime, for example. So think about these different areas that this could be used to, and you need to think a little bit outside of the box, think in a slightly more abstract way. And my advice to you would be to think about how you translate something's happening into the real world. Can you distill it down into these sort of simple individual level rules of thumb that could then display this sort of interesting behavior when scaled up? So once you've come up with a few ideas, so have a chat, bounce around some different ideas. Once you've had a bit of a chat about that, I want you to pick one. And as a group, I want you to work up a design for that automaton. So you'll need to think about things like what your grid is going to represent. So what is that grid representing about a real world system? What's going to be the dimensionality of the grid? I wouldn't advise probably going beyond 2 dimensions, although you may wish to. Although if you give me a 10-dimensional cellular automaton, my head might explode, I think. Think about how many different states you'll have and what all those different states will represent. What kind of neighborhood you'll use for yourselves, what rules you'll use. And again, remember, with cellular automaton, the key is you've got very, very simple rules at an individual level that are leading to complex emergent behavior. So keep thinking, how do I distill that behavior down into rules of thumb? Okay, so to give you a bit of help, so when I did my PhD work, which was looking at bumblebee foraging, that was using agent-based simulation, which obviously is the same sort of principle. But that was looking at things, essentially the bee, each individual bee was just making very simple decisions about, I think this patch of food has this much food in it, this one has this much, I will go to the one with the most. So just very, very simple individual level rules, but then these complex emergent dynamics appear. So think about distilling stuff down, think about motivations in terms of the behavior, and how these sort of things emerge. I mentioned about things like traffic jams. Cellular automata has been used to model that. It's the reason it's been used to show why you get those sort of weird things happening on the motorway where you get a apparent traffic jam and nothing seems to have happened. There's no accident or anything. And it's very often just because of something that's happened with one car that's then essentially caused this kind of chain reaction. And you can use a cellular automata to actually view that emergent behavior. And also think about what questions you want your cellular automaton to answer. So if you're going to build this, what would you want this to tell you? Okay, so at the end of the exercise, I'm going to ask each group, I'm going to ask you all to present your ideas. So make sure you've got somebody who's going to be your spokesperson. And I'm really looking forward to hearing what you come up with. So just let your creativity juices flow, come up with some really interesting ideas. Remember, you don't actually have to build it, certainly not at this stage, although if you come up with some great ideas, I'd strongly encourage you to think about it for projects. But just get those creative juices flowing, have a bit of a think as a group, but have a play first, because it's fun. This stuff is fun, and it's really interesting. It's kind of weird when you think about it too much. So have a play, hopefully that'll get some ideas flowing, and then come up with some ideas. How might you use this stuff? Okay, any questions? No, great. Okay. In which case I will stop sharing there. Feel free to go and stretch your legs, and then I'll open up the rooms now. Get together in your groups, have a play, and then have a discuss. So I'll give you about 80 minutes. In fact, I'll give you a little bit more. Well, no, I'll give you two. So we'll come back at 4 o'clock. So I'll give you a chance to have a break there as well. Okay, see you at 4, and I'll be bouncing around listening in. Hello, everyone. Okay, so welcome back. And it was fantastic, I have to say, to bounce around between the different groups. I've heard some fantastic ideas that have come out of this. Really good that you've managed to really run with some ideas here. And a couple things. So I'm going to get each group just to present on what they've done. A couple things to say up front. First of all, I'm very disappointed that nobody came up with the idea of modeling how to survive a zombie apocalypse, which I was hoping at least one group might. But that's actually a commonly used thing for tutorials for agent-based simulation. So if you're interested, check that out, because it's quite a fun thing to look at. Secondly, before I sort of turn to the groups, there was one thing was becoming quite clear in a lot of the groups, in that you were have these really good ideas and you were wondering whether you could do them within the structure of a cellular automaton. And the answer to that is sometimes I don't know, because technically a cellular automaton is a kind of very pure form of an agent-based simulation. However, the answer is yes, you can do those things in an agent-based simulation, and you'll see in the subsequent sessions in this module when I show you a package called Mesa, and I show you how to build. We use the example of a disease spread, and showing you how to model that. You'll see exactly how you can do all of this, incorporate aspects of time and things degrading over time and evolving over time, and all sorts of stuff really easily. So just before I sort of hand over to you, I just want to give you a bit of a sneak peek at the sort of stuff that you can do, and I'll show you how to do in the subsequent sessions. So I'm just going to share my screen a moment. So this is just a bit of a sneak peek for a preview of what you can expect in the other sessions. So here's an example of what you'll be building up in those other sessions. This is uses a package called Mesa. Really nice package in Python that allows you to build really nice agent-based simulations really easily. It's an object-oriented thing, so you basically set up what an agent is and what a model is and what your grid represents, etc. But it's got all of the concepts of neighborhoods. You just say what neighborhood you want to use, and you've got automatically built-in methods for checking how many people are around in that neighborhood and stuff like that. And it makes it really easy. And it's also got this really neat stuff for capturing and visualizing your grid automatically on a little web server, and so you can build this in. So this is an example of what you can build up really easily, and I'll show you how to do this in the subsequent sessions. So this is just a very simple disease spread model where the big red circles basically indicate people who are infected, the little grey ones that aren't infected. And you can alter things, set up these sliders just for single lines of code saying how many agents you've got in your model, what the probability that they're infected at the start of the model, their transmissibility, so the level of the probability basically that they pass on their infection if they're infected to somebody who's also in that cell, so in the same location. The level of movement, so the probability that they will move at any given generation, and how long on average their disease lasts. And again, we can sample that from a distribution. And so we can run through, and we can have these little dynamic graphs that show, for example, the total number of infected people over time. So in that case, that actually died out really quickly. But if I reset, let's change the number of agents. So there's more agents, more probability of initial infection, longer disease duration and transmissibility, and a bit more movement. So if we do something like that, I reset. So now suddenly we'll see something very different. So you've got lots more infection, as you would expect, and people are starting to get infected. Very few people are avoiding infection, and so you're not getting that sort of dying out. And we also show you how you can sort of model things like the impact of vaccination, and how people then being immunized, and that when their immunity wanes, how that impacts things as well. But you can see it's a really powerful thing, and the stuff to do this is actually pretty simple, and it's really neat to put this code together. So just a bit of a sneak peek, because a lot of you were asking about doing exactly these kinds of things, and the point I just wanted to make is, yes, you can do this, and it's actually pretty easy to do this. So pretty much anything you can imagine, you can put in to an agent-based simulation. Okay, so at this point, I'm gonna stop sharing. Well, I'm gonna get all of the groups to present. So none of you are getting out of it, but I will just spin the wheel to see which order we go in. Just so we're not strictly going in alphabetical order or anything like that. So first up, we've got Holly. So somebody from the Holly group. I will stop sharing. And if you want to present. Just say you're muted in case you weren't aware.
Yeah, we thought about various things, modelling city planning and social media idea spreads and that, but we did revert back to the COVID infection one. So we were imagining modelling it with a few different attributes. So people could be not infected and wearing a mask or not, and then they could be infected and be wearing a mask or not. And we thought it might be interesting as well to have some sort of uninhabited areas, so people on the edges here would have fewer neighbours. We were kind of interested in how it might spread from one area to another. So our initial infection rules we're thinking about, well, we initially said if you're infected, you're going to recover. We initially said if one of your neighbours was infected and wasn't wearing a mask, you would get the infection. But then we got bothered that would spread really quite dramatically. So we thought about changing that to 2 or more with no masks, or 3 or more, even if they're wearing masks. And then we wondered about mask wearing rules, and we thought you could play with them in different ways, but we thought maybe you might choose not to wear a mask because they're annoying and your glasses steam up. But if you've got lots of neighbours that are infected, you think actually COVID's picking up again, I really ought to wear a mask. Or if lots of other people around you are wearing masks, the peer pressure will probably mean, yeah, I really ought to wear a mask. And so we would try that and then play with lots of other attributes like vaccination and, crucially, prior infection. Because if you got infected in one generation, we would imagine you'd be less likely to get reinfected. So that would probably be another attribute that we could include in here. And also, yeah, we did talk about perhaps putting some randomization in there. So rather than you definitely get infected, it would just affect your probability of infection. Yeah, so that's what we did.
Fantastic. Now that's really good. Great. Really nice. Really nicely thought out. I like that. It's you've really thought very clearly about the rules and how you would translate the kind of real world behaviors into simple rules of thumb that you could then put into a Cellular Automata. I think that you could actually code that up in Mesa, and that would work really nicely.
Yeah, we did look for something to do it online, but couldn't find it quickly.
Yes, yeah, I know a number of. I kind of almost wish I taught you Mesa. This is part of the reason I then showed you to say, don't worry, there is a way you can do this. Because I saw so many of you sort of turning to things like Excel or finding little bits online to try and do this because you wanted to actually put it in. So you will be able to do this stuff, and you will be able to code it really easily, actually. So this is brilliant. Really well done. That looks excellent. Thank you very much. Okay, let me share again and spin the wheel. See who's next. Looks like it's going to be Talkie Toaster. Fantastic. So somebody from Talkie Toaster, talk us through your proposal.
Great. So can you see the screen?
Yep, see that fine.
Great stuff. So ours centered around head lice in a classroom. So the grid, as it says here, represents a classroom with students and a teacher. And we were thinking about how might, and within that grid, we would have, each box represents a student's desk, or a student at a desk rather. And the idea was to try and model how might you control or see the impact of an outbreak of head lice. So we used a Moore neighbourhood. We only had 3 states, so you did have it, you didn't have it, or you recovered. I suppose recovered's kind of like didn't have it, but we sort of modelled that through. Our rules were we tried to keep it really simple. So we were thinking though we'd want a probability of catching head lice. You wouldn't be guaranteed to have it, but that would be relative to the number of people, number of neighbours sitting around you that did have it. So so for each yes, you'd have a plus 10% chance of catching head lice, so becoming a positive. And we also talked about a decay function, as it says here, so recovery. So after you've recovered, would there be any margin where you'd be less likely, either through vigilance from parents because they've just recently gone through that process with the child or not. We had a few issues which where we were sort of constrained in this approach. So the teacher, obviously they move around, they're not static at the desk, neither the children, but the teacher more so. So they could be a vector. So how would we model? We thought we'd need to model their movement through the neighbourhood. Also, the children could actually move to other neighbourhoods, so they could have a neighbourhood in the class, in the playground, where their risk may change. We talked about the impact of intervention, so what those might look like. So do we have a letter going out to parents, so notifying them of and asking them to do, be particularly vigilant? Would that have a specific impact? We talked about the sociability of students, and that might change the risk. And then we talked around the questions. So would there be a benefit of introducing a particular policy to try and control it? What's the long-term impact? And does it travel over summer into a new school year? And could we look at the impact of, say, restricting mingling at breaks and so on? So we struggled, I suppose, in summary, some of the concepts that we struggled within the framework of the Moore neighbourhood was time, and also the introduction of a movement of vectors. That was our output in summary.
Brilliant, thank you. No, that's really good. I think that's really creative idea, and I really like the way that you've thought about what the grid represents in terms of that, and the grid represents the children sitting at desks, and therefore that neighbourhood makes sense, and you can think about that neighbourhood. And that's a really important step. So no, that was really good. Thank you. And I think hopefully that you'll see in the Mesa tutorials that much like many of the groups, those kind of ideas of incorporating time, etc., are really easy to do in an agent-based simulation. You essentially just have each agent, which has you could have the remaining days that they remain infected, and that just counts down at each step of the model. And you can do that in a couple lines of code. So all of that stuff you'll see is really easy to do. You go practice it doing that. Brilliant. That was really good. Thank you. Okay, let's spin the wheel once more. See who's next. These are great ideas, by the way. Really great ideas. I'm looking forward. I'm hoping some of these turn up as project ideas. That'd be brilliant. Oh, just gone into Max. Okay, Max is up next.
I could do our first one. So we didn't put anything into grids, but we had a couple conceptual ideas.
Okay, great.
So let me just share this one. The first one, can you see a Word document on the screen?
Yep, you can see that.
Yeah, so the first one is sort of based off of some political theories about collective action and political protest. So the model the thing that we were going to model was a single issue protest. So the grid would be a population with neighbors in a social network, assuming an equal number of neighbors per person, which is obviously a simplification. The states that a person could be would be apathetic, so they don't care about what's happening with this protest. They're aware of the issues, but not protesting. Protesting is protesting, and authoritarian is someone who's sort of anti-protest and wants to kind of suppress the protesting. So we had a few different rules. One is the instigator, which is where an aware or apathetic person will become a protester with just a probability of P. And this is based off of a theory just saying that, you know, everyone has a certain threshold at which they will sort of enter into some kind of political action. And some people have basically no threshold, so they're the instigators. Then we also have the campaigning, where an aware cell becomes a protester when a certain number of their neighbors are protesters. There's disillusionment, where a protesting person might become apathetic if no neighbors are converted into protesters within a certain number of generations. We have education, where an apathetic or an authoritarian cell will become aware just with a certain probability, and then also an education by peers, where an apathetic cell will become aware if 50% of the neighbors are aware and or protesting. We also have this idea of crackdown, which an authoritarian person can turn protesting neighbors apathetic for a certain number of generations. And propaganda turns apathetic people into authoritarian with a certain probability. And the types of questions we were thinking this could answer is how many instigators would you need in a population to make a certain percentage of the population aware or protesting? On the other end of that, what level of crackdown turns everyone apathetic? And we were also thinking about how the initial distribution of instigators and authoritarians would affect the outcome. So if you just had a couple of instigators and authoritarians right next to each other, they might just cancel each other out, basically, versus spreading people around to have kind of a more dynamic state.
Fantastic. That's really good. I really like that. I think that's a really interesting use of cellular automata. And one thing I like about that as well is that the kind of rules that you put in there, you could imagine getting data to support those rules. You could imagine that there would be, you know, for example, studies that would support some of those rules of thumb that you could then translate into about, you know, how people are affected. And so that's really nice. I really like the way that's been thought out. That was really good. Thank you very much. I like that.
We had another one if anyone's interested about smoking
Oh, yeah,
cessation with a similar idea, if Matthew wants to do that one.
Okay, we'll do. I think I've got that one open on my screen. Yeah, just share the screen. So we had similar to before, a grid of people with their neighbours on the social network for a smoking cessation, and we thought this was a bit of a simplification of the to have equal numbers per person, but it might be only the people you talk to about your smoking or smoke with, and we might restrict to younger age groups where smoking might be a contagion due to peer pressure, so we could have peer pressure rules as well. So as with our other model, we also had 4 states here. We had a smoker, a motivated quitter, ex-smoker, and a non-smoker. And so we had these various rules, again, like the single protester issue model. We had peer pressure to start smoking. So this was if 50% of your neighbours smoked, or we could alter it depending on the age of the population under consideration. Peer pressure to quit smoking as well. So, and we thought here it might matter if your neighbours were all motivated quitters or a mix. So you might get mixed messages, which might dampen the pressure to quit smoking. A motivated quitter would become an ex-smoker after a certain number of generations without a change in state. And we have, and then smokers could also become motivated quitters with sort of a spark probability, a bit like these instigators again. And that could be based on sort of seasonal variation, like lots of people give up smoking in January or for Stoptober. And then that could also be based on advertising campaigns, the sort of expected impulse that you want to have on the population. And then there was also this idea of relapse. So ex-smokers and motivated quitters also become smokers with a probability that's an increasing function of the number of neighbours who smoke around them. And then questions we thought might answer, so that thing about seasonal variation, whether advertising could change the status quo in the system. And could you model the formation of smoker support groups by changing the neighbours of individuals, so that you kind of trying to, and then obviously you'd have to check the data supported those rules of thumb.
That's really nice as well. I like that, and I think that that's you could imagine that being a really useful project. And I think so both with this one and the one you showed a moment ago, you were talking about, you know, sort of the neighborhood being a bit of a simplification. So one thing that's worth flagging up actually is that so Sean's network analysis stuff that you talked about last week, you can actually link that up quite nicely with agent-based simulation. So your neighborhood may not be literally just the surrounding cells in an agent-based simulation. You could have it so that your neighbors are defined by a social network that you then set up. So you could combine a kind of network structure that defines your neighbors that then feeds into that agent-based simulation. And that would be a really nice way to look at this kind of stuff, where you've got those more sort of complex neighborhoods. Obviously, where you've got stuff like, you know, proximity of people, then the kind of grid structure works really well. But you can also have stuff like this, where it's less about the grid and more about the kind of social connection. That's really nice. Thank you. I like those ideas. Really good. Okay, right. Let me spin the wheel again. Where are we? There we go. Oh. See who's up next. These are great ideas. Really good. I'm loving this. Fantastic stuff. Okay, so we've got master control program. So somebody wants to share what they've come up with.
Maya, did you want to speak? Okay. Oh, well, that's a no then. So there was only 2 of us in our group. So we did discuss a few ideas, but we did come back to COVID-19 and the sort of spread of disease. The other one that we did talk about, and I don't know whether it's worth just mentioning, was the kind of it was to do with sort of genetic conditions and the spread of genetic conditions, and how long. But we couldn't quite figure out how to sort of put it into a grid and work out the rules based on a population. So also, I guess it'd be kind of interesting if anyone's got any ideas on that.
That's interesting. You could imagine, you know, sort of your grid is a bit more abstract, but with some thinking, I think that could be quite interesting. Yeah.
Yeah, I think we were thinking of it as quite granular, and that's probably where we got stuck. So we talked about initially we started talking about how the level of infection is driving the kind of number of mutations of the disease, but we realized that we were trying to encapsulate 2 different attributes within the state. So we were trying to kind of cover the level of infection and a type of variant, and so we kind of cancelled the variant idea and went back to just a level of infection. So our grid was there were sort of regions in a country or a city. We thought we needed 2D grid. We considered the different states as being kind of you know, low, medium, high, but we ended up going back to sort of 0 and 1 just to keep it really, really simple. And we said our rules were sort of, there'd be like a threshold for the number of neighbours that had you know, COVID infection above a particular level, and that would in turn turn you from 0 to 1. And I guess we kind of ended up, we didn't really consider actually what would happen after 1, you know, if that would change. And yeah, we used the more neighborhood because that seemed to make the most sense. And I guess what we thought about how you could sort of make it a little bit more interesting and answer questions around implementing like lockdown or other rules as well around, you know, when it got to 1, and then if lockdown was implemented in areas around you, so maybe that could be another state, then would that drive down the level of infection around as well, and how quickly could that take? Yeah, I think, I don't know if Maya wants to add anything, but I think that's kind of summarizes what we talked about.
That sounds really good. I like that, and I think that's a really nice, again, really nice use of agent-based simulation, that you can, it's exactly that kind of question. And it's again really creative with the way in which you sort of interpret those things. I always think agent-based simulation is a great one if you really like sort of the creative aspect of model development. Agent-based simulation is for you, because you really have to kind of think creatively, and it can be really fun to sort of put these things together and think about how you represent your real-world system in this kind of more abstract sense. And then you get this fantastic visualization coming out of it as well. So that's really nice. Yeah, so thank you. That's great. Okay, let's spin the wheel again. We're running out of selections. So who's next? Looks like it's going to be Hal. Yeah, Hal 9000. Okay, someone from Hal.
Yeah, I'm just going to share my screen. I don't think we kind of discussed various models, and it's all about infection spread. Well, we kind of have two main models. One is infection, one is something that's very dear to my colleague, which I will leave my colleague to describe. But one is the infection spread, and we started off as a really, really simple one, infected or not infected, and then rules like if you have 3 or more neighbors who are infected, then you're becoming infected. If you're not infected, if infected and if infected, then you will become not infected after 2 generations. And then we kind of went into a bit more complex, infected after 1st generation, infected after 2nd generation, and not infected, and had rules for those. And then had even a more complex one with infected, vaccinated, infected, not vaccinated, and the variations of those and different rules. And another one which kind of exposed the influence of vaccination, again, a more simpler one, vaccinated or not vaccinated, and how that has an impact. And for this one, I will leave my colleague to explain.
Hi. Okay. Thanks, Emma. This is going back to something I did in my PhD quite a while ago, and it was published in the Journal of Simulation. But it was about we were out in India and visited a new clinic in a very remote rural area, and we had data on how the use of the clinic had spread throughout the neighboring villages. And I'd always thought that agent-based modeling could be used to see how the usage spread. And I called it, well, the growth of trust in the clinic, because the people in this area it was a clinic for maternal health and infant health. And the people in the area weren't at all used to having checkups with a midwife or something like that. They just used local people would help, local women would help pregnant wives, pregnant people, but it wasn't, there was nothing formal. So it was very much a growth of trust. And then small village, so the basic unit in this model was villages. Either the village was using the clinic or not using it. And there was the clinic as well. We were thinking geographically, so that was our neighborhood. So any village close to a village. And for this modeling, I had 4 alternatives for how trust could arise in a village. The first rule was if a village close to the clinic was using the clinic, close if, sorry, no, got this one wrong. If the village was close to the clinic, then it would start using it. That's a possible trust factor. Another trust factor was the village had actually been using it sometime in the last 3 generations, and then it would have trust in it. It could trust the clinic if there was a neighbouring village using the clinic, and it could also trust the clinic if there'd been some recent development work in the village. So that it was if the hospital that was running the clinic had done some development work, and that could spread the usage of the clinic further afield. So these are the 4 rules for trust, but I think this was just an initial thought about the states, because there was also there's really 2 things going on here. There's trust and there's using the clinic, and the trust factor, it would be random, as there was a randomness about, even if the village as a whole trusted the clinic, then it would be there was a random factor applied to whether the clinic was being used or needed. So we weren't quite sure how to develop this further, but anyway, yeah, it was nice to think about this. So thanks very much.
No, that's really nice. I like that. Thank you, Honor. And I think that's a really nice example of something that I heard in a couple of groups actually, and something I certainly didn't make clear, in that when you're developing agent-based simulations, we often think about our agents as being people or animals, or some sort of living being, and very often that's the case, but it may not be at all. So here you've got examples where essentially your agents are villages or clinics, and so you can have that kind of structure, that you're not necessarily limited to thinking about people and the way in which people behave. In fact, your agents may represent something else. So that's a really nice demonstration of that, and certainly with the Mesa software, you'd be able to sort of do that and build that in really, really nicely. Fantastic, thank you very much. Okay, apologies, I know we're very slightly overrunning, but we've only got a few more groups left. So there's some great ideas here. So if you can hang on for a few more minutes, I think it'd be great to hear them. So we've got Deep Thought coming up next.
Okay. So obviously we did consider the zombie apocalypse, and then decided that was so cliche that we'd obviously go with something else. No, we didn't actually, but we settled on just a situation, actually pretty random, but just allow bang occurs outside. Some people obviously see that it's just I don't know, a firework or something else, but others don't know what's going on. And we defined there were sort of 3 broad states that people were going to be in. They were going to be informed because they knew what it was. They were sort of just going to be in general ignorance, and then there would be some who would be quite anxious and enter a panic state. And we essentially created just a simple set of rules depending on what state you were currently in. So if you were just in your normal inverted state, if you're surrounded by informed people, then you yourself would become informed, but you only actually needed one panicked person to enable panic to ensue, given that it's quite contagious. Likewise, if you weren't completely immune from panic, if you were informed, if you had enough people around you panicking, then that too would induce panic. And then the final state was for panicked individuals, is that actually they could be returned to a normal state, assuming they were surrounded by sufficiently informed people. And actually we were desperate to try and have a go and play with this, as I think some other groups were. And we too couldn't really find anything online. So basically, predominantly thanks to the application of champions, that is Excel, we, and by we, obviously I mean Martina, in our group, managed to code up a set of cell rules, which basically comply with our rules for the study. So this sort of first scenario where we have a cluster of informed people by the window. Most of the rest of the room is in a normal state, and we've got a few panicked people towards the end. It actually doesn't take many iterations for that panic to spread. And in fact, I think we just did 6 rounds, and pretty much, other than the kind of little cluster of informed people that are kind of holding out, pretty much the rest of the room just, you know, succumbs to panic. And then we tried some slightly different options, perhaps smashing more informed people around. And this time you see sort of slightly different patterns. Still, panic is, because of how easy it is for panic to ensue, that does still tend to take over, but there's slightly more informed people in the room. And then the final set, where we had far fewer, we just had a couple of panicked people, there was more opportunity for, you know, the informed people to establish. Still, panic, because of the rules, still, you know, kind of quite easily propagates, but there's definitely a bit more of a steady state by the time we get to our sort of the final round. We only looked at 8 rounds, but so it was actually, this was probably the most fun, because it's such a visual tool, and I think we found that there's quite a lot of power in that, in terms of being able to see these events unfolding, which really just helped us understand the process and what was actually happening a lot more.
Fantastic. No, that's really good. Apologies, by the way, just as you were starting, I got kicked out of the meeting, but I managed to get back in quite quickly. I think this is brilliant. I think this is really, really good. It's a really nice use of cellular automata, and I think as you said, the real power of the visualization there, even, you know, just using trying to fudge it in Excel, it's really nice that you can see the visually powerful thing of what's going on there. I like that. I think that's a great use of that. And as I say, in the future sessions, you'll be able to see how to code that in Python. And you could indeed code that and see what would happen and be able to play around with some of those parameters. I think that'd be brilliant. Fantastic. Thank you. I thought it was an excellent idea. Okay, let me share again. Actually, well, maybe it's because I keep sharing. I'll just spin the wheel and I'll tell you who it is. That might be the easiest way. Let's see. Okay, so we've got, oh, it's gone on to Skynet. So someone from Skynet, do you want to present what you did?
Yeah, I can do that. 1 second. So our idea was for the sort of the spread of an idea. We picked everyone talking and watching Tiger King in lockdown. So we were going to do a more complicated model where we had whether they'd seen it and whether they liked it, but we found it really hard to do in Excel. So we just said, if 3 of your neighbors are talking about Tiger King, then you will be talking about it. And then there's a sort of passe feature where once 6 of your neighbors are all talking about it, then you don't want to talk about it anymore. And we said potentially you would have like a resurgence. So maybe after 10 cycles, if it came back around, you might talk about it again. But we didn't put that into this. And we also talked about a rebel factor. So some of the people in the group were saying, you know, when they hold fast, like if everyone around them is talking about or watching something, they specifically don't want to watch it because it's, I don't know, not what they want to do. So we had a small grid here, and then you can see the spread, and then you get sort of a hole in the middle of the larger group where it sort of dies and no one wants to talk about it anymore, but then a new group is being created here. I feel like most of what we discussed was already covered by the protest and the panicking group. They were quite similar sort of spreads of ideas. But yeah, we said potentially like Netflix, or someone might want to use it to target who to push certain content to and to measure how popular things are.
Yeah, no, it's fantastic. Really nice, idea that. And in fact, as I mentioned when I went into your group, that you've stumbled on something which is a sort of known to a model called a base diffusion model, which is basically modeling where you use cellular automata agent-based simulation to model the spread of ideas and the spread of influence. And it's really an interesting and powerful tool for doing that kind of thing. And of course, you can, you know, you're right, you could do it for stuff like this, but also you could imagine other things. I think there was one agent-based simulation I saw many years ago that used it in America to model the spread of the way in which different doctors took up certain drugs and how that would influence certain drugs to prescribe and how that would influence other doctors, and how that spread out using agent-based simulations was really interesting. So yeah, it's a really interesting area, really good for cellular automata. Fantastic, thank you, that was great. Okay, I'll spin it again. We've only got 3 left. Let's see who we've got. It's gonna be Saint number 5 up next.
Hello, I'm going to try and share my screen. Bear with me a second.
Yeah, sure.
Okay, so and we did well, it was sort of a virus, a generic virus in a classroom environment. Can you all see that?
Yeah, I can see that fine.
Sorry, I'll move another way. Yeah, so it was a virus in a classroom environment. We just created the grid, represents desks in a classroom. It's probably too many in reality, but we wanted to sort of give it a bit more chance to spread and that sort of thing. So the blank cells are not infected pupils. Red is infected on day 1, and then we assume that there was an infection period of 3 days, so day 2 and day 3, and then after which time they became immune. And then our assumptions were down here, so all the rules. So if you had 1 infected neighbour, there was a 30% chance of being infected. If you had 2 infected neighbours, there was a 60% chance of becoming infected. And 3 or 4 neighbours, you were definitely going to become infected. We used the von Neumann grid as well, so we didn't include the diagonals. And so after infected day 3, you became immune. So what we did was we started off with just 1 pupil becoming infected, and then we used a random number generator here to look at each cell around it in turn, and we worked from left to right down the grid. So after 1 iteration, we got 2 people becoming infected around this person. And then, we gradually moved on, and we did do quite a few iterations. We had quite a bit of time, so we continued, and we actually managed to get all the way to the end. So the blue is basically people being immune, and then we got to know for the spread at this point. And what we noticed was that even though it was randomly generated, the probabilities, that we never actually got to a person having 3 or more neighbours. And it seemed to be that you'd end up, we sort of had 3 people, an increase in the number of infected being sort of 1, 2, and then sort of staying around 3 for a little while. So that's the red ones. And then it drops off and then goes back up to about 4. So it stays at 4 infected every time for quite a long time. And then before it gradually drops right off. And actually there's no further spread at that point. Yeah.
That's really interesting. Thank you. No, that's really nice. I like that, and I like that. Like with the headlights one, you've kind of thought about what the grid represents. That's a kind of a meaningful grid in terms of how that spread. And I like the way in which you've sort of got a bit of insight out of that as well. And so that the fact that you never go above 4, maybe that in a real world system could tell you something. And does that mean that therefore you could then potentially isolate that small number of people, and then how would that affect the spread going forward? And you could test that out in the model as well.
Yeah, we did think the immunity might create some sort of a barrier, but it never actually did. Just when we thought we were getting a barrier, the spread got around it.
It's really interesting about barriers. In my PhD with the bumblebee foraging stuff, it was basically looking at whether bees can spread, sort of cross-contaminate GM seed with non-GM seed. And actually the best strategy, it turns out, is to basically have a sacrificial shield around your non-GM fields that basically the bees can pollinate, and it kind of protects everything else. So that idea of having a barrier comes up quite often in agent-based simulation. Fantastic, thank you. Another excellent idea. So just 2 left. So apologies for overrunning, but these are excellent ideas. So we've got Robocop up next.
So we decided to look at modeling a disease through a hospital, or a disease outbreak through a hospital. Can you see my screen?
Yeah, I can see that. Okay.
Yeah. So it's just some notes. We thought about laying it out on a grid, and the grid representing more the movement of patients and staff between units rather than kind of the actual physical layout of the hospital. So you might end up having some units that have a particularly high movement of patients through kind of towards the middle of the grid, and some of the other maybe wards further towards the edges. The states we had were negative and positive. We thought about a quarantined unit, so it might be shut to new admissions, and patients might not move out of it, and that would influence kind of how it impacts its surrounding cells. And we also started to think about asymptomatic units, so ones that were maybe positive for the disease, but no actions had been taken yet to slow that movement down. The neighborhood method we thought would be a von Neumann method, and you'd be able to run this a generation per day. The rules we thought might be useful were if a cell's positive, the adjacent cells have a reasonably high likelihood of turning positive in the subsequent generation. If cells remain positive for a certain number of days, maybe the cells surrounding them would be put into quarantine. And then the final rule was if a cell has become quarantined for a certain number of days, it would then turn negative eventually. And the idea of that would be kind of if you could deep clean the ward, eventually the pathogen wouldn't be there. And some of the questions that a model like this might be able to answer would be kind of, are you in a phase of the outbreak where it's still spreading, or will it come to a natural end, or are you in some kind of cycle where it will fluctuate for a kind of indefinite period of time? And then things like would adjusting the quarantine period have an impact on the spread of the outbreak?
Brilliant. No, thank you. I really like that. That's a really nice idea, and I could see how that could actually be used. You could build a model like that, and you could imagine that as an HSMA project, indeed. And I could imagine that's the sort of thing that could be used, and that's a really nice, potentially impactful example of an agent-based simulation. I really like that. That's really nice. Thank you. Excellent. These are excellent ideas. Okay, so I don't need to spin the wheel, so we've only got one left. So we've got Marvin. Somebody from Marvin. Do you want to present your ideas?
Yep, I'll just share that. Let's see, where are we? There you go. Yeah, so we went with the infections, spreading of infections. Ours sort of went a little bit down the apocalyptic route because we had dead as a state, but we were sort of thinking about looking at the effectiveness of whether herd immunity would be effective, like something that could be relied upon. We ended up sort of discussing it more than sort of mapping anything on our grids. We sort of talked about probability of spread of the disease, although when we actually sort of put it on our grid, we were just looking at how many neighbors around the original, it's like patient 0, and how it spread from there. Yeah, we sort of got hung up a bit on whether to use the von Neumann or the more neighborhoods. We're sort of wondering how do you actually decide which is the appropriate one for what you're modeling. And yeah, I think that was sort of where we got to, really.
Okay, no, that's great. That's really good. I like that. I like that a lot, and it's again really nice use of cellular automata. You thought about what the different states are, the grid. That's really nice. Just to answer your question, actually, I mean, that's a really good question about how you decide on your neighborhood, and there's kind of no hard and fast rules for that. Basically, you need to think about the key thing you need to think about is what your grid represents, and that's often quite difficult in an agent-based simulation. You need to think about those aspects. What does your grid represent? What does it mean to be in this cell versus this cell? And what does it mean if somebody in this cell interacts with somebody in this cell? And so once you've worked that out, what your grid represents, then your sort of choice of neighborhood should then make more sense, because you can say, well, what are the what's the radius of the interactions? How can people interact? What to what neighbors, given that's what our grid represents? How would they interact within that? So it was really nice. Obviously, a couple of the groups looked at using the grid as kind of desks in a school classroom, and so then you can think about, well, what choosing your neighborhood based on that and how that works. So yeah, working out what the grid represents is always a tough one, but it will help you to then think about what that means, what it means to be in that cell, and then what it means to interact with others, and then therefore what your neighborhood should be. So it's a bit of an art form, but again, it all comes back to this idea that it's kind of creative form of model building. But really well done. That's really nice. I like that. I like that a lot. And well done to you all. And apologies we overran, but I was determined I wanted to see all these ideas because they are absolutely all fantastic. Really, really well done. You've done amazing work with this. I'm looking forward to hopefully seeing some agent-based simulation project ideas, because I think there's some really good stuff in there. And I'd say if you come along to the other sessions in this module, I'll show you how to use Mesa, which is a really friendly package in Python. And I'd argue it's friendlier than SimPy, actually. You get, as you can see, you get some really nice visualizations and all that stuff. It's so great to see that you were all itching to do this and actually make these models real. And you'll be able to do that with Mesa. So hopefully you can join us for that, and I hope to see some great project ideas. So really well done today. Fantastic work. Apologies, it's been a slightly longer day than usual. Next week, obviously, we've got 3 different days of sessions, and a lot of stuff on machine learning next week, and particularly on ethics in AI. We've got starting on Tuesday, and then on Wednesday and Thursday we go into some of the more deep stuff about AI and machine learning. And peppered around that, you've also got some of so Tom's posted up his stuff around forecasting, which is also on Tuesday morning, which will be so Tom's posted the instructions, so make sure you check that out. I've updated the link in the calendar invite now to join Tom's call for that. And you've got a pre-recorded session on the geographic modeling. Just make sure you have a read through those notes. I've copied and pasted that from what Kerry posted last year. So the way Kerry ran that session, which is an amazing session, by the way, on QGIS, it sort of walks you through. There's no code involved. It's all click and drag and drop. So you're pleased to get a bit of a break from that. But really nice software that you can follow along, and the handouts there, you sort of just follow along with that. You do have the benefit that because it's not live, you'll be able to sort of stop and pause and rewind. But Kerry's an excellent teacher, and so you'll find that really good, I'm sure. Fantastic. Okay, I'll close off there because we've overrun far too much. But have a great weekend, and I look forward to seeing you all next week for even more HSMA training. Fantastic. Thank you. Goodbye.